So today we have Dr. Sandoshi Balakrishnan. Dr. Sandoshi is the head of research and development partnerships at AFNIC, France. His research is in the area of networked computer systems with current interest in IoT, identity management, security, and privacy. He has been an invited IoT expert at the European Commission, representing the European CCTLD community. He is also the IoT expert reviewer at CAP Digital, right? IoT working. He is also the IoT working group co-chair, and he is also currently as the DoRA, part of the DoRA Alliance Academic Working Group chair. He actively participates and contributes to standardization and associated organizations such as GS1, LoRa Alliance, IETF, RIPE, and AIoT. He received his PhD in computer science and networks from the University Paris at Marie Curie and is an advisor for PhD students. He is the author or the co-author of 21 plus peer-reviewed articles. We are glad to have with you, Sir. We welcome you and we request you to start the sessions. Over to you.
Hi, good morning. Thank you, Dr. Balaji, for inviting me for this advanced training program to present here. So I hope you can hear me.
Yes, sir.
You can hear me?
Yes, sir, very much.
Yeah, okay. So I will try to share my screen for my slides. So I need permission, it seems.
1 second.
Yep. Yeah. So can you see my slides?
Yes, sir. Maybe you can go into your full screen mode.
So you are not able to see the full screen. Okay.
No, we are able to see other things also, like our notes and the slide deck also. We felt maybe nine.
Okay.
Yeah, yes, this is perfect.
Is it okay now?
Yeah, perfect.
Yeah, thank you again, Dr. Balaji. And so it's quite early morning here in France. So the objective for me when you invited me was to focus on privacy. But I thought that as this is the first presentation, I thought I could give you an evolution of the DNS protocol from plain text to how it has evolved in adding security as well as privacy. So I have a number of slides. So due to time constraints, I will go a little bit faster. If you have questions, we can have it at the end of the session. So the agenda for this presentation will be that we will start with the DNS as it is, how it was designed in the early 1980s, and we will follow a DNS query response, what happens when a DNS resolution is done. So we will see how the query passes through the different places in the internet and gets back the response. Then once it is done, we will see how there have been efforts being done to add privacy into the DNS protocol. The next step is to look at how security layers are added to this DNS protocol. Finally, I will conclude with a tool called Zone Master, which we are developing with the Swedish registry, and how it could be used to verify the DNS health of your domain names. So already Dr. Balaji gave a short introduction about me. So I finished my engineering from the University of Madras, and I did my master's and PhD here in France. Currently, I work with the French Network Information Center. So it's called AFNIC, Association Française Nommage Internet et Coopération. So we manage the internet domain namespace for France. So officially, we are the .fr registry. We manage not only .fr, but also the domain names for overseas territories of France, like Martinique, Guadeloupe, etc. We are also the backend operators for different generic top-level domains like .paris, etc. Since we are managing the internet domain space for France, we are delegated authority by the French government to manage this space. And since we are doing this, we do have a lot of how do you say that, responsibilities with the stakeholders, such as the French government. We have other stakeholders like the African countries which are francophone. We help them. We help them to manage the internet resilience. We do research and development. So at the French Network Information Center, we do have these activities to make the internet stable and resilient. As my other things, I also am LoRa Alliance Academic Working Group Chair. So LoRa is an IoT technology, and LoRa Alliance is a group of companies, like 500 companies from Amazon to Google to Microsoft, which are part of this alliance to develop the LoRa technology, which is an IoT technology. It comes under the LPWAN, Low Power Wide Area Network Group. So that's it. So let's get into the DNS. As you know that AFNIC, the French Internet Network Information Center, the core technology for us is the DNS. So we have an understanding of the DNS protocol and we work on it. So that's where my role here as a presenter comes into play. So as you see before, when you see before the DNS, so what we do see here normally in the DNS is the RFC 1034 and 1035 that explains the DNS protocol and specifications. So sorry for my explanation here, but to have an understanding, I hope everybody knows already RFC's request for comments. So it is the documents, the standards developed by the IETF, the Internet Engineering Task Force. So before the RFC 1034 and 1035 written by Paul Moka-Patrice, the idea behind the DNS came in RFC 791. So it was in 1981. So as part of the DARPA development, the protocol, where the internet evolved, John Postel from the University of Southern California, at that time, John Postel was the one who was managing the internet namespace. So what we see here now see as ICANN, IANA and all. So John Postel was a single authority doing all those things at the time. So when you know that, I'm sure that most of you know about DARPA and how the universities, the industries work together to develop the internet protocol. So at those times, to communicate between each other, they did have the IP address and they needed the domain names. So, the domain names are for easy understanding for human beings to identify a network address. So at those times, they used host.txt, a file which was shared between each of these institutions when they were updated, and it was difficult for them to manage the host.txt file. So at that time, they wanted to have something that was more easier. So in RFC 791, the network protocol design ideas are discussed, and addressing and naming is one of the discussion in the RFC 791. And there, John Postel says that, so he concludes, he resumes the internet in 3 sentences. It's like you have, you want what you want to seek. So it's identified by a name, and the information regarding the name is in the address. So it's somewhere stored in the server, and it is the address that indicates where it is. So from the name to the address, you have a route. So you have to route from your name to the address to get this information. So he resumed it in such a simple way, which gives you an idea why DNS, even now after more than 40 years, is still the basic cornerstone of the internet. So if you see the DNS, it could be called as a mapping table, it could be called as a phone book of the internet. So if you come to the third point here, we have the identifier, the name, which is understandable, which is remembered by the humans very easily. And that name, it has to find the route where the applications are. For example, here, the applications are the mail ID, the web server, etc. So it is identified by an address. So to go from the name to the address, you have the mapping table, which we call the naming service, that is the DNS domain naming service. So the domain naming service to work, there is an infrastructure behind it. Okay, so it's not just like in our phone where we just add the name and the telephone numbers. So there is an infrastructure behind it which works it, so to make sure that the domain name is resolved wherever you are. You could be from the India, you could be from France, you could be from Australia. When you resolve afnic.fr, you will resolve to the same information wherever you are. Whatever type of operating system you use Android, Linux, Mac, but it's the same information that is available to you. So that magic is done because of an ecosystem behind the domain naming service. So the ecosystem starts with the number one here. So the identifier is standardized. It not be something random, but it's standardized. So the ID identifier, that is the domain name, and the IP address, it is standardized by the IETF, that is the Internet Engineering Task Force. So the identifiers domain names, they have the system, and the IP address, they have another system. So that's for the domain names, we call the domain registry. And at the top, it is ICANN. So we had somebody from Samir and Gupta from ICANN presented early. So ICANN manages what goes in and out of the root. So we have like 13 root servers, and we have Anycast servers all around the world. So what goes into the root server is managed by ICANN. It's true that they have a multi-stakeholder ecosystem who helps them to manage that. And under that, we do have a layer where we call the top level domains. And in the top level domains, we have two varieties. One is called the CCTLD, country code top level domains, like .fr, .in. We have GTLDs, generic top level domains like org, .com. And under that, we have the second level domain names, and we could have multiple layers behind, down it. So the beauty of DNS is it's hierarchically managed, and it could evolve, scale, and it gives the performance. So in this domain namespace and the registry, it is managed in such a way that, for example, a name is not duplicated. So afnic.fr, there is only one afnic under the FR hierarchy, but you could have an afnic.com in another sub namespace. So that's how the provisioning is done. So this is what we call the route. In John Postel's sentence, we see a name indicates where it is, and route indicate how do you get to the address. So the route for the domain name registry And similarly, you have for the IP address, you have a hierarchy where the top, like ICANN in the domain registry, you have the IANA, and under the IANA, you have a different layers. For example, when you in India or CDAC, they get the IP address, they get it from the local internet registry or from the ISP. But the local internet registry gets the IP address located by the 5 RIRs, regional internet registries. For example, in Europe and Middle East, we have the RIPE, Reserve IP European. For in the Asia, you have EPINIC, Asia Pacific Network Information Center. Similarly, for each region, for example, for South America, you have LACNIC, Latin American Network Information Center. For Africa, you have AFRINIC, etc. So this ecosystem makes sure that the identifier, that the domain name is resolved to the IP address without any difficulties. So let's go to a classical internet use case. How do you do it in a classical internet use case? Is that a user accesses the web. So at the first, he types something in his browser. For example, http://cdac.in. He doesn't know what happens behind. There's a black box, and he gets the information, the website information of CDAC. So the first thing that happens here is a DNS resolution where you get the IP address of cdac.in. Then once you have got the IP address, a HTTP connection session is established to get the information. So this is the classical internet use case. So let's go a little bit into the steps. This is what the first point in the agenda where we are following a DNS resolution. So let's say we are typing iot.rd.nic.fr. The browser searches in its cache. So the browser always has a cache to make it performance. So whether it has the IP address of the domain. If the IP address is not found, what happens is it asks the OS, operating system, to resolve the IP address. In the OS operating system, you have a small program which we call the stub resolver. The stub resolver gets this information from the browser, saying that it wants to resolve iot.rd.nic.fr's IP address. So there are different sub programs inside the OS, which starts with nsswitch.conf, where it defines how this resolution happens. It has, for example, it has like files, DNS, etc. The files is the etc host.file. So it says that by priority, it will go and look at the files, that is etc host. It looks at the etc host. It sees that it has only the names of localhost and Santosh, but not iot.rd.nic.fr. Then it goes to the next resolve.conf. And in the resolve.conf, we have the IP address of our resolver. For example, a normal user will have the IP address of his ISP, Internet Service Provider. But here we will, as a company, you can have your own name servers where you have your own resolver. So you go and ask this resolver to find the IP address of iot.rd.nic.fr. So what happens is that it gets into the resolver, and the resolver, it has to find the IP address of iot.rd.nic.fr. If the resolver doesn't have any information in the cache about this domain name, so what it does is that it goes and asks the root. That is the root service. The root says that, okay, I'm looking at a scenario where this root, or these are called authoritative name servers, and this name server doesn't have any information about this domain. So the root will say that, okay, I don't have any information about the domain, authoritative information about the domain name, but I do know that you can go and ask the top level domain.fr, who will have information about it. So this is called an iterative query, but from the user to the resolver, it is a recursive query. The recursive query is that you have to find the information, but from the resolver to the root, it's an iterative query because it finds only the partial information. So the step goes one by one until to the rd.tic.fr, and from where the IP address of the domain name is found out. So that is the authoritative information. So that is found. So if you see here from a Wireshark perspective, the Wireshark is a tool to see the dump of the packets that happens here. So there are multiple queries that is happening here. So 10.10.86.48 is the local private IP address that I have. And we have, this is 10.10.50.163 is the IP address from looking from our company's point of view, but it has its public IP address. So there is a up and down transaction happening until you get the IP address of the iot.rd.nic.fr. So this is how the resolution happens. So before the resolution to happen, there is a lot of discussions that is happening on that we don't see outside. So if you see in the Wireshark, it's how the datagram is constructed from the Ethernet frame to the IP to the UDP and DNS. I'm not going to detail. From a wire format, you have, this is the packet form information. So the source address, the destination address, the port is 53, and the DNS packet where the query is for iot.rd.h. This is the transaction ID. So these are all, the yellow color is the one which shows which is important for the DNS packet. So in the DNS packet, you have a header packet and you have the payload. So in the header packet, we have the query name, the opcode, the ID, the query count. The query name is iot.rd.nic.fr. The query type is it's asking for an address, and the query class is the internet address. So I'm not going deep into that. So let's see what happens. So the packet starts with it goes to the root, and in the root, if you see it creates a query ID. It has a question count. So it's a query, and if you see here, this is recursion desired. So it's a recursive query where it's asked for a recursive code. So that's what happens at the beginning. Then when you see the response, you see the recursion is not available, that is 0. So the query is, there is a response. But if you see there is no answer, so there is an authority count which says that these are the name servers that could have information about iot.rd.nic.fr, and you have an additional count which says which are the IP addresses of these authoritative informations. So what I want to show here is that there's a lot of data and metadata that is being transmitted between a query and a response. So similarly, you go one by one. I will not go deep into that. So until you get the response. Okay, so this is what the answer count is that. So you have the final information. So the answer count is 2. And here it says that for this query, we have the response, that is the IP address that has been asked. And this is the IP address. And this IP address is obtained from the name servers ns3.nic.fr and ns2.rd.nic.fr. So this is how a query transacts from a web browser to the different parts of the internet and gets back the IP address. So it's a big black box for us, but what we have to see is that there are a lot of information out in the internet which we don't see. Now, until now, what we have seen is that how a classical DNS query response happens. Now let's go in a little bit into the privacy. So privacy is defined by Wikipedia as the ability of an individual or group to seclude themselves or information about themselves and thereby express themselves selectively. So if I want to look at it from an easier point of view, so To get an information, you need to identify yourself. That's needed. But do we need to identify to everybody all those information, or we need to identify only to a certain person to get this information? For example, if you are going to the doctor and you have a issue, a health issue, you want only the doctor to know that problem and get medications for that. You don't want the secretary of the doctor to know that. You don't want others involved to know about your problems. So similarly, in the internet, what happens is that everybody knows about your problem. For example, if you are going to buy something, let's say alcohol in the internet, if you search for a website and that website that you have searched is known by the top level domain, by the root server, by the second level authoritative name servers, all these people know that somebody like Sandosh has searched for alcohol in the internet. So is that necessary? So if you see this image, this is by Jeffrey Stern, who is a famous researcher at the Asia Pacific Network Information Center. He has done some measurements and he shows that what we think is that we have a client, you go to the DNS resolver and you get the DNS response. That's not how it happens in the internet. There are a lot of, as you've seen in the Wireshark that I've shown before, there are a lot of other queries being done, and these stamps of information about you are there in the internet. For example, if you see here, this is from the TC dump of the root server. And if you could see somebody with the IP address, 2001 IPv6 address of 2001.67c 1348 8002 has asked for a query called armanpress.am. So for the root server to know this, it's not necessary. So, and another issue in the DNS is that all the information is clear text. So anybody can see what happens. DNS resolution, as I said, by this image, it's quite talkative. And your information could be used for business intelligence as well as surveillance. For example, if you see, if you are searching for something on Amazon, for some product in your Google, then immediately if you see in your mail, you get a mail from Amazon saying that these types of products are available. So this is all information collected. So that's the business intelligence that happens there. And we know there are a lot of state actors who are using DNS information for surveillance. So there have been a lot of discussions in the internet. In the IETF. The IETF is the one which creates standards for all network protocols and above. And we know that the discussions had started for a while, and I will show you how this timeline has happened. But before that, what I would like to point from this slide is that, inference could be done from these DNS queries. So my colleague, who is a famous, is one who wrote the RFCs for DNS privacy. What he says, for example, is that currently, if you want to know what Pentagon does, you have to just go and sit near a pizza shop near Pentagon. And if you see there are a lot of pizzas being ordered by the Pentagon, and then you can infer that currently there is a war going on in Israel and there is a support from Iran, and maybe Pentagon is trying to do something on Iran. So it's not the authoritative information, it's an inference that you can get from the data that you collect because of more pizzas being ordered from a pizza center near Pentagon. So that's an inference. Similarly, this is a paper from Princeton, which shows that based on DNS queries, you can infer what type of IoT devices that you're using. For example, these are the queries that we have on the right, and the devices that could be used at your home. So this gives more information about the individuals that are staying in the home. There has been a lot of research studies like that. Even there is a issue in the Dutch parliament where they stopped smart meters for a while because a research pointed out that based upon your electric meter at your home and the consumption, that can infer what type of series that you are looking in, whether you are looking at Netflix, what type of ideology you have, right or left. So these are all the things that could be inferred from this information. So that's why it shows that DNS queries could give a lot of information, data and metadata that could infer about a private individual. That causes an issue in privacy. So if you see with privacy, there have been 3 RFCs, and all the 3 are written by my colleague Stephen Botsmeyer at Daphnic. So the first RFC 7626 talks about the DNS privacy considerations. It mentions how the DNS data is out in the wild and how cache snooping, DNS cache snooping could be done between the stub resolver, between the user and the resolver, how the information could be collected from the naming servers and the authoritative servers like the root servers. Then he suggests an idea which could minimize the information that is out in the wild. It is called QName minimization, query name minimization. It is RFC 7816. It's an experimental RFC because if you know at the IETF, you have a standard variety, you have an informational variety, and you have an experimental variety. So after RFC 7816, there were a lot of research being done on QName minimization at an operational level. People have implemented that. There are also academic papers, and based on these feedback, RFC 9156 updates the DNS query name minimization RFC, which obsoletes RFC 7816. So what does QName minimization does? When the iot.rd.nic.fr, it goes from the stub resolver to the resolver. So the resolver knows that the guy behind 192.134.4.85 is interested in iot.rd.fr. But the resolver doesn't send the complete query during the iterative state. It sends only FR to the root. It says, okay, do you have information about FR? And the root says, yeah, you can go to the tld.fr. So similarly, the metadata that is sent with the query is minimum. So thus, like what I have seen earlier, the root server doesn't have information about iot.rd.nic.fr is asked by whom. So query name minimization minimizes the amount of data which has been out in the wild for DNS resolution. Now, how do we configure QName minimization? So as you all know that DNS, there are a number of DNS softwares which uses the same protocol. So we have bind, unbound, not, and others. So in bind, for example, if you want to add QName minimization, you have different options like relaxed, strict. When it means strict, if the resolver that is getting your query doesn't use query name minimization, then the resolution doesn't happen. If it is relaxed, the resolution happens even if there is no query name minimization configuration in your resolver. If it is off, it is a normal DNS plain resolution. Similarly, in unbound and not. So I did a small test with the dig. So I tested with 2 name servers, government name servers in the internet. For example, ns2.winavi.net is for Telangana. Is for Telangana, I think. So I tested whether they have the resolvers, the open resolver, whether it uses QName minimization. If you see, I use the QName test domain to test it. QName minimization is not enabled. So they don't have this option enabled on the resolver. But I did another test with, for example, the open resolver by Maharashtra government. So you see, QNAME minimization is enabled. So you can see which resolver to use if you don't want more information of yours to be on the internet. Now, there is another test, that is another study that was done by Princeton. In Princeton, to improve privacy in the DNS, they used a concept called oblivious DNS. So the idea is to obfuscate the information that is out in the wild, as we have seen earlier. So what happens here is that when a client issues a DNS request, the stub resolver here you see, it generates a session key. It's a symmetric session key. It encrypts the domain name with the session key. So if you are asking, for example, afnik.fr, it encrypts that domain with that session key. Then it sends that information to the ODNS resolver, public resolver. To do that, it adds with afnik.fr the ODNS suffix. So once it is done, it sends it. The stub sends the query to the recursive resolver, which then sends to the authoritative name server. These are the authoritative name servers for the specified ONS domain. So these people doesn't know, because it is encrypted, which domain name is being asked. But the ODNS resolver will have information because it has a symmetric key to encrypt and decrypt. So it is also added with the public key. The ODNS resolver gets all this information and it responds back to the ODNS stub. So all these people, they don't have information on what query and what the IP address that is behind that query. So oblivious DNS has been there for a while. It has some issues of operational implementation. As I understand that some like Cloudflare are using oblivious DNS. They have support for oblivious DNS. But I don't have much more information. But it's a method also to improve privacy in the DNS. So we have seen the DNS clear text, what happens. Then from a privacy point of view, there are two options here where we have query name minimization as well as oblivious DNS. If I'm going above my time, please tell me how much more time do I have, Dr. Balaji? Pardon?
15 more minutes.
I didn't hear you clearly.
Hello. Yes, sir. 15 more minutes, sir.
15 more minutes, so I will go fast. Okay. So now we will look at it from a security perspective. So if you see from a security perspective, what happens is that here it's the DNS resolution, and then here is the information. You get the web site. So attacks could happen here, such as the Kaminsky birthday attacks, which is called DNS cache poisoning, etc. Here also attack could happen. So where you have, for example, here the security is done by TLS, transport layer security, and you have the certificate authority. And if you compromise the certificate authority, you might be able to compromise this resolution. So as you know, DNS spoofing is that, if, for example, you poison the cache with some other information. That is, when you are asking for afnik.fr, before the afnik.fr gets into your resolver or your stub resolver, you can do a man-in-the-middle attack so that you can identify the transaction ID and send a false IP address back. Or you can poison the cache by putting another IP address in the name of that, and then you spoof the resolution. So to counter that, we had a DNSSEC. So in the DNSSEC, I will not go much into detail due to time constraints. So the idea simply is that you have for example, you have the address record 192.68.0.1. You have also a encrypted version of that address record. So once you get back into that, you compare the IP address that you obtained is the same based upon DNSSEC. So there is a method. So will take time, but you have a trust chain that is being created. And if you want to compromise with DNS, you have to compromise the complete trust chain. So that's a little bit difficult. And similarly, the verification is done based upon this trust chain. So DNS trust chain, DNSSEC, what it adds is that it doesn't encrypt. What it adds is that it makes sure that it enables you to validate the integrity of the information that you got. So you have a clear text information, you have an encrypted information. So you compare the clear text and encrypted information to validate the integrity of your response. So this is how, I will not go details due to time constraints. So DNSSEC, we know what we understand here is that, so it adds a security layer where you can make sure that the IP address that you obtained is the correct IP address and it is not spoof in the middle. So that's the capability of DNSSEC. But there is another attack scope here where you have the certificate authority. If you know, for example, we use the certificate authority to get the, for example, the IP address. It is certificate by the certificate authority Kinetics, and this is the fingerprint of the certificate authority. The problem with the certificates authority is that in your browser there are about 1024 root certificate authorities. So these root certificate authorities stamp the information with the, for example, this is validated by me. If I have to go more clearly, it is like, for example, if you go with the passport to a to a immigration authority, it's the Indian government that stamps that the Santosh Balakrishnan is, and the photo is validated by the Indian government. Similarly, afnik.fr, the IP address is validated by Kinetics. But the problem here is that there are 1024 root certificate authorities, and if you are able to compromise any one of them, you can compromise the complete resolution of the web service. So this already happened, where there are famous attacks like Komodo and DigiNota attacks. What happened is that they have a compromised certificate authority, and based upon the compromised authority, they were able to get credentials for Google Mail and all, and they were able to see the real Google Mail. So this was done during DigiNota. State actors were involved. So the IETF started discussing it, and they came with a response which is called the DNS authentication of named entities. So the DANE protocol is already in implementation. It is currently more used in the mail scenarios. In web, it has not succeeded because due to performance issues. So the browser vendors like Chrome, Firefox had some plugins really, but they stopped those plugins and they are not deployed in the browsers. But there is currently a working group which is called DNS authentication of network clients everywhere, which is trying to see whether DANE could be used in other scenarios, not only for the mail. So what does DANE do is that, for example, it has a fingerprint of the certificate authority. So that's called the TLSA resource record, Transport Layer Service Authentication Resource Record. And if you see, for example, what happens is that you can, once you get the certificate, you ask the DNS also about the fingerprint. So you validate the certificate with the fingerprint that is obtained from the DNS. So thus you reduce the scope. If you are only compromising that single authority, you will be able to compromise this resolution. Otherwise, you will not be able to compromise. Like earlier, if you compromise any of the one root certificate authority, you'll be able to compromise. So that's the difference here. So I'm not going deep into that, but what happens is that the attack scope is reduced. So you could compromise only by attacking the particular certificate authority. So with DNSSEC and DANE, security is added to the clear text data communication done by the DNS. Even for IoT purposes, now it's being used. It has been updated in TLS 1.2 and 1.3 for mutual authentication here. So when you do the TLS handshake, the server and the client both can ask for DANE indication. When I say DANE indication, not only for the asking for the IP address, that is the A, it will also ask the TLS resource record, which is a fingerprint of the certificate authority, thus enabling you to validate your HTTP or certificate information. So another thing that you see here is that in the RFC 7626, which it talks about the DNS privacy considerations, it looks at how DNS is too talkative, and also there could be different occurrences. This is one that I got from a colleague. So for example, he tries to resolve ether.com.tr using RIPE Atlas probes. So one of our earlier presenters were also talking about how to look from India from a different angle of from different network spaces to identify how the resolution is done. So it is already done by RIPE Atlas. So RIPE Atlas, it's free. You can ask RIPE for an Atlas probe, and you can put anywhere. So, and you can also use the RIPE Atlas to do measurements from the different parts of the world to have a look at how things happen. So he does that about 500 tests. And if you see that out of the 500 tests, for the same domain name, there are different IP addresses. There are 5 occurrences of different IP addresses here. There are 6 occurrences of different IP addresses here. So that is called the lying resolvers. So there are certain resolvers, when you ask them, they lie the information that, and then they try to snoop you. So here also, if you see, he did the same. There are about 498 probes, and 463 probes were giving the correct IP address, and the other 6 probes were giving refuse or serve fail. So there are some type of hijacking is done, or information, or it is being restricted. So I think ether.com is some domain name which was sensitive in Turkey at that time. So that's where my colleague did this experimentation. So what we want to show here is that resolvers can lie sometimes, and may allow you to snoop. So this is the DNS encryption timeline. I'm not going deep. So this is how things have been done. So I will go to the how. Now, until now, we saw minimization, Corona minimization of oblivious DNS for privacy. We saw how DNSSEC and DANE enables security, but the information is not encrypted yet. It's always clear text. To encrypt, there are 2 protocols that has been added, which is called DNS over TLS and DNS over HTTPS. So DNS over TLS, what it does is that it does the transport layer service thing, not only for the HTTP resolution, but also for the DNS resolution. So there is a secure handshake that has been done earlier to make the communication encrypted. So this is how a classical TLS handshake happens. And once you have the certificate being added, then the DNS query and response is done. So if you want to configure DOT, you have to do this. The left side is for bind, and the right side is for unbound. So you have to add the full chain, and then you have to listen on port 853. So that's how web dot communicates. Similarly, in unbound, you need to have a forwarding resolver which uses supports dot to do that. Okay, so I tested with the Cloudflare for me, and I saw that I was not supporting DNS over HTTPS or DNS over TLS. So then I added the configuration in my browser, and I could see that DNS over HTTPS and DNS over TLS is supported. Then I did a test with my with the KDIG. It's a not dig, and what I could see that all my communication is encrypted. Similarly, if you see from Wireshark, you see that the TLS handshake happens, and then the communication here, you don't see the domain name. So there are problems with DoT. One is that it uses a specific port 853. So the middle boxes can block it or identify that anything that goes, it's encrypted. So that's an issue. And performance is also an issue. As you add security, you know, DNS is a datagram UDP layer protocol that is mostly used, and it has been used for a purpose to enable performance. But here performance comes in problem. With the DNS over HTTPS, the advantage is that there are no two layers of handshake that may happen. It's a single handshake, TLS handshake, both the DNS resolution and the HTTP resolution is done. So that's how DNS over HTTPS enables and adds, reduces the performance issue. So if you want to configure DoH, for example, you can do that in your Chrome. You go to the settings and the security DNS. As of now, you can use Cloudflare, Google, or your own private DNS resolver, which supports DoH. And once it is done, you can have normal secure encrypted communication. For example, here, if you see, you can see all the information that is without DoH, what I'm asking, how it is being done. But with the DoH being added, I could encrypt the payload. There is an issue here. So I tested with Quick. Quick is another protocol that's also encrypted by, it has been developed by Google. Normally here, if you see, it should be DoH, but I had a wrong screenshot here. So with DoH here, in the place of DoH, a Quick, it would be DoH. So that's how it is there. So finally, so what we have seen until now is that DNS is the plain text, adding privacy with QNAME minimization and oblivious DNS, showing that the integrity of the DNS responses are correct. So we have DNSSEC. We have reduced the attack surface in the HTTP using DANE, then added encrypted communication with DoT and DoH. So how do we test it? So, you know, DNS is a peculiar thing, like it's similar to our body. For example, in our body, we could have certain issues somewhere. For example, you could have diabetes, you could have kidney, but still you will be living. But if you want to make sure that you are completely correct, then you need a complete health check. Similarly, for DNS, you will be accessing the information even if there are certain issues, but it might cause problems somewhere. So that's why you need to test all the different issues, for example, connectivity, delegation, name server, DNSSEC, all this. So like in the health check, you need to have a testing of different subtopics to make sure that your DNS resolution is completely correct. So this is how you do with a normal test with a normal tool, basic tool. But if it doesn't have information, it will get only no error, next domain, etc. But you could use ZoneMaster. ZoneMaster is the tool developed by Afnik, my company, as well as the Swedish Internet Registry. We have been developing it for the last 10 years. And I could say with all humility that it is the best tool for a comprehensive health check in the world. So you have the complete information and it is updated. There are about 4 or 5 people, dedicated people working on it. And with each evolution of the DNS, those things are updated in the ZoneMaster. So you see, you have the different subtopics that we test. It's completely free, open source. And you have different ways of getting this information. You can use a CLI if you want to. If you can use a Zone GUI like zonemaster.net. If you want to have your own database and all, you could use that. You can test thousands of domain names using the batch method. So there are different outputs, and you could get statistics. So I'll go a little bit speed so that I'm on time. So here, this is how, for example, I tested a domain name where you can see that the domain is resolvable, but there are issues. Connectivity, for example, if it says that over TCP, you don't have connectivity. So when you resolve over UDP, you might get the information, get a response back. But when it falls back to TCP, you might not get the response back. So similarly, you have a DNSSEC issues here. In the delegation, for example, there are child does not list enough name servers. So for redundancy purposes in DNS, you should have at least minimum 2 name services. So this is not happening here. Similarly, here we have another test which shows that there are errors in DNSSEC that could cause real serious issues. So with Zone Master, it is possible for you to identify different issues with your DNS zone. So sorry, I had to go a little bit fast to be in time. I hope I was clear. If you have any questions, I will be happy to respond.
Yeah, thank you, sir. Any questions? Right, so it appears there are no questions. Thank you for walking us through the complete evolution of the DNS protocol from its plain text nature to the secure and privacy aware nature, which is the present state. Thank you very much, sir. Vale sir has left for joining an urgent meeting. So we'll be getting back to you, sir. Thank you very much.
Thank you. Bye.
Thank you. Bye. Santosh sir, are you there, sir?
Yeah, I'm here. Hope I am audible. Am I audible?
Yes, sir, you're audible, sir. Sir, here we have Mr. T. Santosh, Scientist F from the Internet Governance of MIT Division. Sir has been very supportive for us throughout the tenure of this project, and he has been encouraging us in doing this work in the research on DNS. Sir, over to you, sir.
Yeah, so thank you, Gopinath, for the brief introduction. So good morning, all the participants over here, and this is a day for you. And I can see that there is a police officer also. So I will start with the issue from the law enforcement side on domain name system, which is called DNS. So as my previous speaker, who also has a same name, excuse me, who also has a same name, but written in a different way. So he has explained what is a plain text DNS and what are the encryption standard. So the thing is, I believe the participants mostly are from the Indian industry and Indian academia. And in case of Indian academia, you must have learned a bit in your computer BTech or in MTech classes about this encryption. Am I right? Can we have any response from any students over there? Have you heard about this? DOT and DOH? Now, who has made these standards? Who is responsible to come out with this kind of a standard? Another question, can we have a say in this type of standard? So, any answers? Unable to hear. Gopinath?
Yes, sir.
So, are the participants, have they heard about this? Who is responsible? Yeah, so maybe my previous speaker or earlier, all the speakers might have said. So the Internet Engineering Task Force, which is IETF, which is part of the Internet iStar organization, is responsible for coming out with these standards. So the problem here is the Indian contribution. I again emphasize the Indian contribution towards this standard is very minimal, which is only 2.3%, right? So I urge all of you to understand which are these standards, how it is affecting people. Yes, it has many pros and cons. My previous speaker might have told about the privacy factor which bring in the encryption, that is well good. But he might have explained about DGAs, that is domain generating algorithm. Have he explained? So there are many algorithms which generate domain names randomly. Say like 1000345.com 100. So it comes with many permutation combination by which the fraudulent people masquerade, right? They use it for fraudulent activities. So basically, I'm not going into deep. I'm just giving an overview that DNS abuse, domain name system abuse, has been and is being discussed across the globe. How to mitigate it? So there is another organization which is responsible for the domain names. They are responsible for the protocols as well as the DNS, which is called ICANN, which is Internet Corporation of Assigned Names and Numbers. Now, there too, the participation and contribution is very minimal. So, the point which I would like to make it is that the domain name system abuse is a big problem, not only for India, but across the globe. So, if you can Google it or you can note it down. What is a DNS Abuse Institute? Okay, so there is a DNS Abuse Institute which is mostly which is in Netherlands, I believe. So Netherlands is a country which are actively contributing towards DNS abuse. Okay, so can we have a DNS Abuse Institute in India wherein which you people all can collaborate on it? I believe that you have the expertise, but there is only a few, a few inputs to be provided to you so that you can, you can execute it. So in Netherlands and the countries like US, they have this domain name system abuse institute, which provides the data set that these are the domain names. So I believe domain names are the main tool which is used for fraudulent purpose. Okay, so I am thankful to CDAC Bangalore to have the training with the support of Ministry of Electronics and IT, as well as the National Internet Exchange of India, to provide you the training. And this training has to happen on a regularly basis, right? And through this training program, I would request all of you to go through ICANN, just Google it later, and also IATF. A standard can be on with your name, because you might have written papers in IEEE. Similarly, you can write standards. Okay, that is IATF. So I'm leaving it with here, and this is a problem statement. And I believe that there will be a big industry coming on this, because cybersecurity, yes, it is a big issue, but domain name system is the major problem statement for the cybersecurity professionals. So all the best for all the trainees, and please learn it thoroughly so that you can be one of the master trainers and lead our country ahead on this mitigating DNS abuse. Thank you once again, and over to you, Gopinath.
Thank you very much, sir, for the encouraging words and emphasizing on the necessity of IETF, ICANN, and India's contribution to the internet drafts and protocols. Thank you very much, sir. Sir, we'll get back to you. Thank you. So it's a tea break now. Tea will be served on the other side. We'll just open this door. It's a 15-minute tea break. We'll resume the session after the tea break. Yeah, good morning, everyone. So let's start the session and hope I'm audible to the online audience also.
Yes, sir. Yes, sir.
Okay, thank you. Yeah. Okay, right. So I'm Gopinath. Right. So I'm Gopinath, and I'm part of the RISE group here, the cybersecurity group in CDAC Bangalore. And this session, which is on detection of algorithmically generated domain names. In short, they call it as DGA. Will be presented by me and Mr. Chanakya, the colleague of mine. Okay. Right. So this is the outline of the session. We'll try to understand what is domain name. Of course, we had a good introduction in the previous session where we understood what exactly is a domain name, what is the DNS protocol, working of DNS protocol, what is plain text, and what is secure and privacy in DNS ecosystem. All these were understood in the previous session. But we'll start again in this because there are a few who may not be, who may be very new to this. So we'll understand what is domain name as the first part. And then we'll have a look at understanding the DNS ecosystem. And then we'll understand how a DNS query, what actually is a domain name and how a DNS query gets resolved. And then we'll understand domain generation algorithms, DGA. And then we'll understand the harmful effects of DGA. What are the harmful things which are associated with the DGA? And then we'll try to understand the working of a DGA in the DNS ecosystem. We understood the DGA and then how a DGA works in a DNS ecosystem. That has to be understood. And we have done some research on DGA and by extracting some features related to the DGA, domain generation algorithms, and we have detection approaches for that. That will be the discussion point towards the end of the session. Okay, right. So, what exactly is a domain name? This is our portal. This is our website. coednssecurity.in is our portal, our website. Publicly available, and of course we have many tools, and our work, most of our work is listed there on the portal. We keep updating the portal on regular intervals. So this part actually is called the domain name. This part actually is called the domain name, the block part. Okay, the remaining is just the URL, and you have the path and the resource which you finally reach out to, right? So this is the domain name. So the DGA speaks about the randomness in generating this domain. Okay, that is the randomness associated with generation of that domain name, mathematically generating that domain. Okay, so that is what is a DGA. Hope the message is clear that URL is different, and a part of the URL, the most important part of the URL to identify a machine in the internet ecosystem is what is the domain, right? So this is the name of a machine in the complete internet ecosystem. And you have asked for this resource, which is residing on this machine. So when you try to hit this URL on your browser, the request first reaches this machine, and then it traverses to this file to retrieve it for you, right? So that is the way it works, to make it simple. So DNS ecosystem, if I put the whole Ramayana in one line, it is like, you give a domain name and you get the translated IP address of that, because internet works using IP addresses. Internet can't understand domain names, right? So internet works using IP addresses. So the name is given for the human convenience. People have to remember the domain name which they want to visit. So this is for human convenience that we have a domain name. But finally, internet works using IP addresses. So this IP address has to get translated into its corresponding IP address. This domain name has to get translated into its corresponding IP address, and that is what a DNS ecosystem in a single line it does. Okay, there are many other related things that happen in the DNS ecosystem. A few of the things we'll be covering as part of this session, but the primary work is this translation of a domain name into IP address. Okay, let's try to understand DNS ecosystem. First is a domain registration. Okay, let's say that we don't have a portal coidnssecurity.in registered in the DNS ecosystem. How do we get that registered and make it available on the internet ecosystem, right? So that is what is the first step. So I want to register a domain name coidnssecurity.in, right? So first registration process, I am the registrant. I want to register my domain name coidnssecurity.in has to be registered, right? So I approach one of the registrars. There are many registrars in the market. You know that. Nixie also operates on the .in registry, National Internet Exchange of India. They operate the .in registry. So coidnessecurity.in is actually registered with the .in registry because you have .in at the end of it, right, which is operated by the Nixie. I approach the registrars, those who have the access and those who have the means of verifying whether this domain name is already present in the ecosystem or not. Right, that has to be verified because the internet can't be having duplicate names, right? The names have to be unique. So the registrant wanting to register coidnssecurity.in approaches the registrar, and I register my domain name. Ask for registration of my domain name with the registrar. There are many registrars around. So the registrars will check for the availability of the domain name, and if it is available, they'll go ahead and take some charges for that. There are various resellers starting from 200 rupees, 300 rupees per annually, or 500 rupees annually, or 1,500 rupees annually, depending on the service that they give, right? So they'll go ahead and register the domain name, which is coidnssecurity.in. Okay, so what my requirement is that I'll have to identify a machine where I can host the contents of my coidnssecurity.in, and I assign a public IP address for that. I need to purchase a public IP address and assign that IP address to that machine on which I have hosted my coidnssecurity.in, right? Okay. So once that hosting is done, if this registration happens, it's go live, right? The domain name or the website coidnssecurity.in is available for the audience to access on internet, right? So these registrars are the people who have access to the complete database. They can check for the availability and they can register the domain with the database. Okay, this is called the registry database. It is the registry, like there are a few people who are in the who have passed through the 1990s or 1980s. I hope you recollect the telephone directory book, right? As similar as this registry, it's like a telephone directory book where you map a domain name with the IP address, corresponding IP address, and that is stored in this database, right? So this is the registration part. Once this registration is done, it is live and is available for the internet audience to access it, right? So now, how does the domain get resolved? A person wanting to access coidnssecurity.in, how does it get resolved? A user visits coidnssecurity.in. I hope it's visible. Okay, all right. Right. So the first access to any domain name will end up at the recursive resolvers. Okay, at the closest recursive resolvers, and which recursive resolver is going to be contacted will depend on the service provider we are connected with, right? We have several service providers starting from BSNL and MTNL. So depending on the service provider, the closest recursive resolver will be accessed for knowing the IP address of the website coidnssecurity.in. Okay, right? There are a few more detailing which is just to be done between these two and further also, which we'll do in the further slides. So these recursive resolvers then contact something called as name servers. If you recollect the previous session by Dr. Santoshe, it said that authoritative name servers was the word he used. I have used the word name servers. Both purposes serve the same purpose. So name servers are the one which have access to this database. So if you recollect again, we had registered a domain name with this database. And now we are trying to access the same domain name using the internet, right? So when you are trying to access the same domain name, the name servers are the ones which are privileged to access this database and fetch the IP address for the CODNSSecurity.in and return it to the user, so that user in turn can directly hit the server or the machine which is hosting the CODNSSecurity.in and access the resource, internet resource, right? Now here is the catch. DNS ecosystem is a complete business environment where there's there are many stakeholders, and there are many entities which work in the DNS ecosystem or the internet ecosystem. So they have, and we often how internet exactly is open is that this is the registration part. We know that, okay, right? When it comes to the access part, we have two primary entities which are involved there. One is called the recursive DNS servers, or we call it as DNS resolvers, or the caching servers, we also call it. So one is the recursive resolvers and the other are the name servers, okay? And in this globe, anyone has a freedom to host their own recursive resolver or their own name server. They have their own freedom to host that, okay? So just imagine when someone has the freedom to host their own recursive resolver and become a part of the internet, and or they host their own name server and become part of the internet, the amount of vulnerability that the internet ecosystem has can be imagined, right? So that exactly is the issue with this ecosystem. It's just to encourage the openness of internet that they have this policy, as Mr. Santosh had earlier addressed, that internet is open and it is managed by ICANN, an international non-profit body. So they have given the freedom of hosting this recursive resolver and name server for anyone. Okay, if I have the capital, I can purchase a server, or even a desktop machine is okay. I can host my own recursive resolver, or I can host my own name server. Okay, it's not necessary that my name server has to be registered only with the name servers which they are providing. Okay, right? I can host my own name server and give an IP address to that, where finally a user visiting CODNSSecurity.in will end up in my server which I have hosted. Okay, right? So that is the primary part of it. So this is the wholesome picture of a DNS ecosystem. Okay, right? So now let's try to have a little more of detailing to this part. Steps in resolution of a DNS query. DNS query meaning I want to access a domain name and I want to know the IP address of that domain name. Okay, right? So you CODNSSecurity.in. Okay, user visits CODNSSecurity.in and wants to resolve CODNSSecurity.in. By resolve, I mean to say that given the domain name, I want this IP address. I want the location of the resource, internet resource in the internet, right? So every machine has its local cache. Okay, every machine has its local cache. Every operating system maintains its own local cache. So if I'm regular visitor of CODNSSecurity.in, my machine itself will be having the mapping of the domain name to its IP address, right? So my machine will directly hit the CODNSSecurity.in machine, which is present on the internet, and access the page form. Okay, so my call ends there. I'm now able to access CODNSSecurity.in and it's available, state available. But it happens only when there is the machine is a frequent visitor of that website and the mapping to that domain name to IP is present in the local cache of the machine itself. Okay, this is the first case. Now, let's say that local cache doesn't have it. The operating system doesn't have, or the machine does not have the value of IP to domain name mapping in its local cache. Then it reaches out to the closest recursive resolver. As already said, it depends on the closest recursive resolver is associated, right? So it depends on the service provider. There are plenty of service recursive resolvers. India has about 98 or 99 of them. So there are plenty of recursive resolvers. So it will reach out to the closest recursive resolver and ask for the value. Recursive resolver is also mentioned as a caching server. So recursive resolver also has a local cache. Okay, right? So the mapping for the CODNSSecurity.in with its IP address will be checked for in the recursive resolver's cache itself. And if it is present in the local recursive cache, then the call immediately returns from the recursive resolver to the user, and the user, this is the IP address of CODNSSecurity.in, and the user can straight away hit the server, okay, access. So this is the second hop where the call can terminate. Now the third case, let's say that recursive resolver also doesn't have the value in its local cache, meaning in some time period, some earlier time period, there was no call to that specific recursive resolver for the domain name. So it means that it does not have the entry in the local cache, right? So in that case, it will start traversing something called as the DNS hierarchy. Okay, there's a DNS hierarchy which starts from the root server, and you have the TLD server and you have the SLD server. It may go further also. So it will start, recursive resolvers will start querying the DNS hierarchy. It will start by querying the root server, which we call as the dot, which is represented using a dot. And that dot, the root server, the recursive resolver will ask the root server where exactly the dot in is present. This is the domain name which I'm looking for, codnsecurity.in. So this domain name will be read from right to left, in the reverse, from right to left. So from the right, I find in. So I need to find out where exactly is .in. So the first query from recursive resolver to the root will be where exactly is .in present, .in's name server present. Okay, name server meaning a server which is capable of providing address of something. It's not the resource, it's not the internet resource. It is a server which provides location of some resource, right? So the first query from the recursive resolver to the root server is asking for where exactly is .in name server, right? So recursive resolver will respond back saying that this would be the name server of .in, some IP address it will return, right? So, and further, recursive resolver will contact the .in name server and ask for where exactly I can find COIDNS security.in, right? And it would have the entry and it will return back the name server of COIDNS security.in, right? And then the recursive resolver will contact the name server of COIDNS security.in and ask for the IP address, right? So here the IP address of COIDNS security.in is returned. And when this is returned, recursive resolver will store the mapping of the domain name and the IP address in its local cache and return it to the machine, and the machine will be able to access the internet resource. Right? So these are the 3 stages of resolution of a domain name, right? So as already said, recursive resolver and forget about this root server and forget about this TLD. This SLD name server, second level name server, can be hosted by anyone. Okay, right? So this recursive resolver and this SLD name server can be hosted by anyone wanting to join the internet. Okay, so and here are the primary vulnerabilities associated with that. Okay, because this root server is managed by ICANN, nobody can make an entry into a root server without the intervention of ICANN. ICANN has of course outsourced to few agencies, because there are many root servers across the globe. There are about 1,600 some root servers present. So, so ICANN is managing this. So we can't interfere in this root server. Whereas the TLD is managed by the TLD managers. Each TLD has its own managers. So TLD is managed by them. The final level SLD or the level below that can be managed by anyone in this way, right? So that is the final picture of a resolution of a DNS query. Okay, right. So coming to the actual topic of this session is algorithmically generated domain names. As the name suggests, in the previous case, we had a domain name and we were registering the domain, right? Just imagine that if I automate this, meaning on the fly, I generate a domain name, I register that on the internet and make it available for access, right? So, okay, so that is the idea of algorithmically generated domain names. So if you recollect few of the attacks like Mirai botnet or WannaCry, which happened in 2016 and 2017 time, they were frequently connecting with a CNC server, command and control server, right? So they were victims of botnet attacks, and they were connected to a CNC server to get some commands and execute that, right? So conventionally, a few years ago, I mean a decade ago, the mark right? But recently, in the past few years, the manner of operation has changed. So a malware comes with something called as a domain generation algorithm. Okay, it comes with a piece of program which can generate domain names, right? So the traditional way of operation was a hard-coded domain name present in the malware, but recently they have started employing domain generation algorithms, which comes built into a malware, which gets implanted onto the victim, right? So algorithmically generated domain names are known as DJ domains, domain generation algorithm domains, right? So what exactly is the benefit of this DJ is that, let's say that we have the respective police force here. Maybe they can understand better. Let's say I'm a culprit. I perform some malicious activities or criminal activities in Bangalore. Change my name, change my geographical location, go to another place, perform that criminal activities, again change my location, geographical location, go to a different place, change my name, and perform some criminal activities, right? So by this, traceability becomes difficult, right? I keep on changing my identity and changing my location, right? So by that, the tracking becomes very difficult, right? It is a difficult task to identify the person and track them down, right? And that is what is called as domain fluxing. Okay, I have a machine which hosts an internet resource. I keep on changing the domain name of that internet resource machine, right? Of that. Meaning it means that I'm changing the internet identity of that machine, making it untraceable. Making it difficult to be traceable, right? That is what is domain fluxing. Okay, right. So DJ is basically used for domain fluxing activities. DJ stands for domain generation algorithms. DJ is a program that adversary embeds in a malware binary. Okay, we have a malware which is built by some malicious actor or adversary, and he puts that domain generation algorithm inside the malware and delivers or implants it on the victim's machine. And the job of DGA is to generate a large number of pseudo-random domain names, right? So there it generates a pseudo-random domain names, which actually will be the domain name of a command and control server or a malicious server on the internet, right? So that will be this thing. So a few of the examples are these, which have been previously used as DGA domains. You can see the randomness in them, right? They have numerals. They have characters which don't have any sense of English, right? So we have W here, B here, X here, and few numbers in between. You can't find English words within them, right? And doesn't appear to be a human readable or memorizable domain name, right? So that is such are DJ domains, right? So there are two types of DJ domains basically. One is called the time independent, the other is called the time dependent. The idea is simple. Time independent meaning when the DJ algorithm generates a domain name, it doesn't consider time as an input parameter for that. Okay. Time dependent meaning it considers the time as an input. What it actually implies is that I run a DJ today, it will generate a domain name. I run the same will generate a domain name. If both the generated domain names are the same, then it means that it is time independent. Sorry, it means that this time sorry. It means that it is time independent. Yeah. So meaning algorithm which generates the same name on two different the same list of domain names on two different days is not related to time, right? So it is time independent. Whereas an algorithm which generates different domain names, the algorithm remains the same, but it generates different domain names on different days or time, right? Then it is time dependent. Okay, so it becomes more difficult to trace a time dependent DJ when compared to a time independent DJ, right? So these are the two broad categories. Okay, right. So how exactly this works? Briefly, I'll just narrate in this slide, and the next slide is where there are two slides, one this and the next slide where we can try to understand what exactly is DGA. So DJ works on a seed, something like we have a key, right? Something like we have a key for encryption. Right? Encryption has a key, right? Similarly, a DJ needs a seed on the basis of which the domain name is usually generated. So this seed on the basis of which the DJ is generated is known to two people on the internet. One is the attacker who generates the domain name and registers the domain name. The other is the malware into which the DJ is implemented. The DJ algorithm is implemented, right? So the seed is common between two parts. One is the malware and the other is the attacker, right? So this DJ program seed will be an input to the DJ program. DJ program will generate a pseudo-random string, some string of some kind, wherein you know that a string of this kind will be generated. Okay, and that pseudo-random string will be appended with the TLD. TLD something of like .com or .org or .xyz or some TLD, right? The second level. And then it will output a DJ domain. Now the DJ domain is ready. This DJ domain can be registered and made available on the internet, right? So now this is sequence. So the primary takeaway from this slide is that there is a seed which is common between a malicious actor and the malware which is implanted, right? Okay. Okay. So what exactly has to be understood? Does the internet user, he visits a malicious link, some malicious website he visits, and a malware gets downloaded and installed to this. This is a different subject. How the malware gets downloaded or how it gets installed, that's a different subject. It's not part of the DJ as of now. A malicious website and website. No. Visits a malicious website and a malware gets downloaded onto his machine, and meaning his machine is now infected with a malware, and that malware has the capability of generating domain names at random, right? Okay. So the installed malware on the user's machine and the attacker here both have a seed in common. So malware uses seed for DJ generation, for domain generation, right? For DJ generation. Attacker uses seed for generating the domain names. So both are using the same seed for generating the domain names, meaning on the installed machine, victim machine, and the attacker side, both sides, the same set of domain names are getting generated because the algorithm is same and the seed is same, right? And list of algorithmically generated domain names are available now, and the list of DJs are available with the adversary, malicious actor also, right? And this malicious actor owns a command and control server or a malicious server, and he registers this malicious server using this list of generated domain names. And at the same time, when the registration is active, the implanted malware on the victim's machine queries for the DGA which was generated, domain which was generated at the victim machine, right? So CNC will be accessible during that time. Okay, and they mostly use a hit and run policy. They'll be active for a short interval of time and then go absconding, right? So within the short interval of time, they'll be keeping on changing the domain names for a specific set of time period. And of course, when things keep on changing, when they are dynamic, its traceability decreases, right? Almost zero, right? So this is the working of a DGA, domain generation algorithms, right? So yes, sir. Yes, sir.
Is listing the domain now that DB domain.
Yes, sir.
Where it is registered?
This is a server which performs a malicious activity.
Yes.
And this is a service which performs malicious activity. So this has to have an internet identity.
Okay.
And that identity is given by this algorithmically generated domain name.
Okay. Sometimes it's supposed to be restricted, like earlier you told, no, the restricted are restricted in the display.
Exactly, exactly.
The same way where they able to get restricted, actually, it may not come to all. Yes, PLC restricted thing.
This is called command and control server.
This is meant for only the malicious.
This, exactly. This is no. This is hosted by a malicious actor on the internet. He performs malicious activities using this, and it is dynamically registered with different domain names at different points of time. And that is what
That's what I'm asking. The CC registered you are telling, no?
Okay, it is in the same name server. It is in the same name server. It is in the same name server that the registration will happen. Okay, so this is the conventional DNS environment. So in this, I'm changing the entry, keeping on changing the entry of the domain name for the corresponding.
Yes. That means they are coming and they are registering on the SLD itself.
Correct. Yeah.
Basically, the Mitigation server can be hosted by anybody. So that is why they
Exactly.
and from there
Exactly. Yes, so yeah, that's the part, and so this acts. This makes the system more dynamic. So being dynamic, the identity can be changed repeatedly, and it decreases the traceability. Right. So I think yes.
there are no rules respect to DNS registration on ICANN side. Like I registered my on one of the names. I'm changing it. How big I can change?
Yes, sir, that is for the benefit of the internet, openness of the internet, that they encourage that. But still, there are some registration details that you need to give before while registering, right? So, so the part which I mentioned here, this ecosystem which I mentioned earlier, this is the conventional DNS ecosystem. This is the conventional DNS ecosystem where I need to approach a registrar and I need to register my domain name. And if I want to change the IP address of my domain name, or if I want to move to a different domain name, I'll have to contact the registrar again and update it. So it's a manual intervention which happens. But there is a catch to that. There is another system, alternate system, which is called as dynamic DNS, DDNS they call it, in which this is my machine, and if I change the IP address of this machine, it automatically updates the corresponding name server. There is a DNS client.
Sir, I have a question here. If the gateway firewall is in between the DNS and if I block the plugged in domain, so do it protect the plugged in domains which I have blocked in the firewall?
Okay, you are blacklisting domain name. That is what you want to say, sir?
No,
In your
plugged in domains mean the new domains which has been generated by the bot or whatever the attackers.
Yes, sir. Yeah. So you are adding that to the blacklist of the firewall.
Yes, if it passes by through a firewall. DNS traffic.
Yes, sir. That's very much possible in your premises. Yes. You can do
Thank
that.
you. Thank you.
So
Yes, sir.
DDNS is for changing IP address dynamically. The same domain. I have a domain name. I'm changing my IP address and go to my code and getting that dynamic IP everything. This is happening, but here the problem is I'm generating the domain name itself dynamically, and then somewhere I have to register. If it is a top level or subdomain, then okay. My subdomain, I don't need to register. I understood that. So what I'm trying to say is that these domain names are subdomains, so they don't need registration again.
No, they don't need registration. Subdomains. Yes.
There is one subdomain you can block. Subdomain is common, then can be easily blocked.
Subdomain is common, it can block. Yes, that's possible. Yes, that's possible.
But the example you showed, some domain names in previous slide, you showed some domain names. Example of media. The secondary domain is different.
Which slide, sir?
So it's
Okay. Yeah.
इसमें वो domain is not they don't have the same secondary supervisor. So that is it is
Okay. Okay. Right. So got your point. Yeah, got your point. See, actually, no. In the DDNS, it's possible. There are two types of attacks which are possible. One is domain flux, which I addressed here. There's another called as IP flux, wherein I can change the IP address also. Domain flux meaning I change the domain name. Right? Both are possible. Both types of attacks are possible. Number one. Number two is that, as one of the audience just now pointed out, we have the concept of park domains. Park domains means I take a domain and register it for myself, but I don't make it active. I remain dormant for some amount of time, and so I can time it accordingly, right? So I can have these 4 domains. I can have them registered at different point in different time points, right? So using that, I can use the dynamic path. Okay, so the malware will also get to understand that at this point of time, this domain is going to be active. So because we have the other category, which is called as time-dependent domain. So that is also possible. And the other catch, one of the question was also interesting. It's not always necessary that every DGA domain will be finally resolved. There will be plenty of non-existent domains. NX domain can also be a response. It is not necessary that the malware is so much synchronized that every domain it generates will finally get resolved. It may generate 10 domain names. Out of those 10, it may be able to resolve and make some perform some malicious activity. And 8, it will fall into a non-existent domain, NX domain. That is also a possibility. It's not always necessary that it's 100% success every time. That's okay. So hope this drives across the concept of DGA. And with this, I'll hand over to Mr. Chanakya for the further stream. Thank you.
Hello, I'm Chanakya. Gopisa is my mentor and reporting officer. So some might be wondering like how CNC server is registered, right? So actually, the credit card and IDs can be stolen, right? Yeah. And there are some registers in Cayman and Panama. The laws are like a little bit relaxed, right? So we can register there using stolen IDs. Actually, I got in touch with a docking domain person who takes care of this. So they take care of the credit card details and all. The research can be done on how we can stop malicious registration out. But suppose it gets registered, okay, and it is impacting our system, we'll catch them. Yeah, that's how it is. Okay, so let's say today I go home, download a game, use a pirated software, apply the patch and come to CDEC and connect it to the LAN. The malware can propagate if it is connected to the CNC server and infect the CDEC, although I can bring my laptop here, but the malware can get propagated in the system. Second, suppose the thing of DGA is like, suppose I am the malicious author. I can infect a lot of systems, not only in CDEC or somewhere else in Bangalore, my home place, Guwahati. So what happens is that I have a lot of systems under my control. Now I am making a target vector, like I will attack the CDEC recursive resolver. I can flood CDEC recursive resolver with DNS queries like DDoS attack. So I can make a controlled launch because I have a lot of computers under my control. How am I doing that? I am connecting it to the CNC server and instructing those botnets to flood the recursive resolver of some entity. So that is how botnets attack, and it is helped by the use of DGS. And suppose I have an access to a system that is already malware infected. With the CNC server, I can perform data exfiltration, like silently I will take away the data and all. And suppose I encrypt the system and I can collect ransomware using DGA. So now you might be wondering, like, DGA attack is happening, why not cut the connection, right? But the DGA attack is happening through the same line that google.com is going through, like port 53. Usually the DNS queries goes to, so we can't do that. So we'll have to identify the benign domain from the malicious one. Benign meaning the good one, malicious meaning for our case, it is the DGA domains. Okay, so how does a DGA work? Okay, step 1, 2, 3, and 4, as mentioned here. Suppose I am the malicious author. I will write an algorithm. And as Gopi sir has mentioned, these are the steps of how I will write an algorithm. I have infected suppose I have infected only one malicious malware infected machine I have with my contact. Now I will register the domain name, some domain name, let's say 2-3 domain name I'll register in some registry and host it as a CNC server. Okay. Now there itself benign because nothing malicious is going on. Okay. Suppose the malware infected machine also has the same algorithm and all. It is infected. It is infected by some infected vector, like I have sent some malicious mail in out. I'll send it in bulk. I don't care like one gets infected or 10. If 100 gets infected, I'll be more than merrier. One gets infected, we'll do that for my business, but let's go with it. Suppose the malware infected machine, now its task is like once it settles down, let's say there is a time component, we will try to contact the DNS. So for a DGA, like different DGAs generate different types of domain. Let's say there is one malware configure. It can generate like some variant, earlier variant can generate 40,000 domain names. Also, you might be wondering, like we can catch them using some network administration, right? Network administrator, like, but 40,000 domain name churning out, like which one is the good one and the bad one in a short period of time will be difficult. By the time DGA has done his work and taken up. Let's say the DGA now wants to resolve the domain name of the CNC server. And say this is the domain name that is registered by the malicious author as the CNC server, and he wants to resolve this. While resolving this, he will not only send his domain name to the DNS, but he will send random other domain names to a DNS. By this way, it is masking itself in this DNS queries. Like which one is getting resolved, we can't figure out. Some may get resolved as NX domain because for them, the CNC server is not registered. By this way, it is masking itself and it can get passed to the network administrator, like more or less. So then at some time, it will connect to some form of DGA, and some other time it will connect to some other form of DGA. That's how domain fluxing is. It is changing its CNC server. Suppose I get some red flag that this DNS is connecting to this CNC server, I block it. Okay, no worries. Then the malware will connect to some other DGA, other CNC server. That's how the connection gets established. And it is difficult for a person to get hold of which one is the normal domain name and benign domain name, unless he has some measures on how to detect those domain names. Okay, so we have our own features. These are the features that we can show to you that how we can detect those DGA domain names. We'll come to the machine learning approach and all. Suppose a lot of DNS queries are being sent to the recursive resolver from a machine at a short period of time. We can consider that some kind of red flag is going on as an initial measure. Also, like accessing the same FQDN means fully qualified domain name in the same time window. Like suppose, let's say for an example, some DGA domain ABC, some random numbers .in or .bazaar is accessing the DNS at the same time, like repeatedly, means some connection is going on. We can consider that as a red flag. Okay, so usually what happens is our good domain names like google.com and all, based on our analysis, we can argue on that. Like the SLD, the Google part or Facebook part is little bit small. So good domains have little bit length in small and they have meaningful words. DJ don't have meaningful words and they are little bit longer in length. So domain with length of greater than length of 5 for an SLD can be a malicious domain. Okay, so R data means the resource data of a domain name. Like there is a record which helps the mapping, which gives the mapping information of IP to domain name, MX record, mail exchanger record, which specify the mail server of the domain name, then CNAME record, canonical name record. We can give an alias to the domain name. So when a domain name is getting registered, we have to supply all of these records to a registrar. But usually when the domain name is registered newly for a short period of time, if we have defenses in place, the R data will be usually small and we can catch that as a malicious domain name. NX domain, previous slide that I mentioned is like from a system that a lot of NX domain responses coming, meaning it cannot resolve to an IP address. So that is also a kind of red flag that can be considered as some suspicious activity going on. And recently registered active domain and repeatedly hitting up the DNS is also a kind of red flag. SLD is not in the top ranks, meaning there is some LXR ranking list, Majestic Million ranking list of the good domain names. Usually the public access it and based on their metric, they specify which domain name is good. You can see like Facebook, Google will usually be in the top places, like top 10. So they are good domain names. And if it is not in those ranks, let's say like 500K or 1 million, that can be some sort of a benign or malicious domain name. Also, again, we can argue on that. Wildcard domain names, meaning suppose I register a domain name malicious.com, and in the R record I specify start.malicious.com. That is a wildcard domain name. Now I don't have to register another domain name for a CHC server. Anything in the subdomain for that malicious.com will get resolved to the CNC server. So that helps a lot for the DGA. So we'll see a DGA detection approach. We have been working on our own. This is a generalized perspective of what we have been working on. So suppose I have a DGA, like I get its masking information, I get the binary that it is malicious. Suppose, and I have some resources to manually engineer the DGA. I can reverse engineer that DGA and figure out what kind of domain name it is generating. If I can decode the algorithm of the DGA, it is usually come in binary. This has actually had a lot of disadvantages because malicious author usually gets flooded with a lot of domain names. Like they send us a lot of domain names that might not be of the same pattern. New DGAs get offered repeatedly. So it is labor intensive, requires a lot of resources and a lot of knowledge about assembly. And it can't detect variants like configure version 1 is there today. I think version 5, 6 is there. So if we have a DGA reverse engineer configure 1, it can't detect the version of configure 5. Configure usually is a malware. So we have this, because of this AI, we can use machine learning and deep learning approaches to detect those domain names. Usually you can notice that these benign domains are usually good domain names. Like you can remember them like google.com, facebook.com, and some easy to remember names. But DGAs are actually hard to remember for some random domain names, but things are changing now. We'll talk about that. But basic way is that the domain names can be identified, the DGA ones. So machine learning approach, we can use some feature extraction technique, like those features that I talked about in the previous slide actually are the features of this DGA detection approach only. And once we have the features, we can train and classify the model and detect new variants. I'll talk about this now. Okay, let's say we have a machine learning approach. Suppose I am a benign machine now. I want to access COE DNS security.in here. And those DNS will do its magic and will give me the IP address. I'm happy. Now, I am a malware author. Now, I want to do this. Actually, I will not be going through the browser. The malware will call the DNS through internal processes that is going on. When you open the task manager, you can see a lot of processes going on. It will call the DNS through that. And now it wants to resolve to the CNC server and all. We will have to catch it there. It has infected, we can't do about anything about that, but we'll catch it and flag it as some malicious activity going on. How can we do that? So let's stop it. Suppose I build a machine learning model and I will deploy it in a machine which has a direct access to the recursive resolver, and it will try to communicate with the DNS server. Like whenever a new domain comes, I will try to classify it as a malicious or benign. Now, the DNS queries needs to be returned quickly. We can't do it in a time. Machine learning model usually takes few seconds of time to analyze, like if it is a benign or malicious domain. So what we can do is like, okay, if it wants to resolve to a CNC server, we'll give it back. But within a few seconds, we can verify whether it is a malicious domain or not. Because we'll pass the domain name through the machine, and where the machine has hosted a malicious domain classifier, and the classifier will flag it as a malicious or not and return the query. The query will be returned, but once it is returned, within a few seconds, we'll flag it as a malicious or benign. And based on that, the administration can take some action. That's how we can detect it. It's a generalized approach of how things are going on in our project. And this is the way actually, like when we do a machine learning task, how can we get from the end to the bottom? Like usually we need to gather data. For DGA, there is a lot of earlier there was to have a lot of open source data, but now the data is like money for a lot of people. So we have to buy some data from their organization, or we can reverse engineer those domain names, but that is labor intensive. So get the data from those authorities and clean the data, that is data pre-processing. Feature engineering basically figure out how we can distinguish a domain name malicious, whether it is malicious or benign. And let's figure out like on how many features are useful, like those individual things that this domain name is meaningful, the length of domain name is this for good domain, the length of domain name is bad for that domain. But for 1 or 2 features, we can figure it out on our own. But when the dimension is used, like 20, 30 dimension, then only the machine learning problem or deep learning problem can help us in figuring out like whether a domain name is malicious or benign. And for that, we'll train the model. And based on the model, we'll test the model. And after some time, we'll again check for the validity of our model, like how is the performance deviating with time. Then again, we'll train the model and the things will go on. Yeah, like that. And with this, I conclude the session. If any of you have questions, you can ask me. Yeah. Yeah.
ISP had a better chance of finding DGA than end user.
End user, yeah, we can try end user also, but we are trying to detect in the ISP. But
What we are discussing here is on the end users, like
no,
non organization.
we are discussing it from the perspective of a recursive resolver. The query that let's say you are the author, okay. So you will type some query, DNS. I mean, you want to resolve your IP address, right? So you will go to the recursive resolver, no matter what, you will go there. We'll catch you there.
Create my home.
Yeah.
In my home, my resolver will be from my ISP.
Yeah.
It would be most of the cases, it would be the case with everybody, most of the people.
Yeah.
So ISP had a better chance of finding this DGA. They had a better chance of talking to the DGA.
We can debate on it actually.
And I'll try to answer it. So, the question is that whether an ISP can help in the initial communication. So the ISP is just a service provider. Even though they can add the intelligence of stopping a domain name, again there are many complexities related to a domain name. I mean, blacklisting the domain name or whitelisting the domain name. Let's say that a domain name is genuine, and still by some intuition, ISP blacklists the domain name. Then ISP is going to be interrupted. Right. So for that reason, none of the ISPs would like to do that. It has to reside on the DNS ecosystem, either as the encryption server or the internet gateway of the premises or any of those such applications. Yes, sir. We have developed some tools. Demonstration of the tools and the description will be in the last session of the students. Sir's question was
If there's a ISP system, then I go. So there will be a gateway and from the ISP system. So I can't do all this whatever in this machine. And we posted on the local machine.
Yeah, you're hosting a DNS server of your own. Yeah, but that DNS server should have the intelligence of identifying that. That can be done by, again, that's a capital cost. We need to have a threat model which will build for them to identify that. No, sir, DNSSEC is for the security of the record. It's just avoids DNS spoofing, but or DNS cache poisoning. But we can't add it to a division. That is a different subject. Okay. Any other questions? As per they don't have the intelligence, as per the line, they don't have the intelligence of identifying a domain, but they do maintain a list. If we have a blacklist, we can add to the firewall. One of the participants had a question on that. We can add to the firewall or the UPS, and they can drop that. That's fine. Okay, right. So thank you, Janitya. Thank you. And the next session is on DNS attacks by Dr. Sanjay Adiwal, and Dr. Sanjay Adiwal is part of the RISE team here. cybersecurity team here. He's the joint director, and his area of research is DNS, and he provides many services related to BAPT audits and all. And he has done his PhD from the on DNS security from NIT Surat. Over to you, Dr. Sanjay.
Thank you. Hope I am audible. Audible to online also, online participants. So my session is on DNS attacks. Okay, so let us start directly because we don't have time now. This is the content of this particular session. We'll try to focus on what do you mean by DNS attack and what is the categories of DNS attacks which is there. So we have mainly two categories. Attacks onto the DNS infrastructure, attacks onto the DNS servers, and so on. And second category says that saying that you can use DNS to attack others. So I have one picture image for you. You have to guess the person. Okay, you have to just guess the person. Yeah. So can you guess this person? Any of you? Have you seen this person? No. Okay. I'll tell you, this guy is Paul V. Petris. He is the father of DNS. So if we are talking about DNS, we should know who is the father of DNS. This guy has developed the entire DNS ecosystem, right? And we are talking about DNS, we should know what is DNS. So we all know, right? What is DNS? DNS do what? It does the IP address to domain name translation. Like we have our phone directory earlier. In that we have a name and the phone number, our landline number. Likewise here also, you have domain name for www.cdat.in. We should know what is the IP address of that domain name, right? So DNS is a service which will provide the lookup of the IP address to the domain name. So it does for both IPv4 as well as for IPv6, and it does the reverse also. What they mean by reverse? If you have the IP address, if you want to know the domain name, you can contact DNS and you'll get to know about that also. Now, if you talk about DNS, you have a lot of say components of DNS ecosystem, and you should know how DNS works also. How many of you knows about DNS working of DNS process? Can you raise your hands? How DNS works, sir? Okay. Few of them doesn't know. For them, I'll just have a quick. Yeah. Hello. Quickly, I'll just show you how the DNS works. So you see that if this is one of the system, this is your system at your home or at your office, right? On this system, you are typing one domain name called www.cdat.in. Okay, this is what you are typing here on your system. Now, what happens? All the system knows the IP address, right? Because they are following TCP/IP, where the network there, IP address has to be assigned. Okay, so for this, we need to know what is the IP address of cdat.in. Who will get to know? Your client will get to know. Now, what is happening? How will client know the IP address of this particular domain name or this particular URL? Client will send a DNS query to your local DNS server. So you might be having your ISP has been provided one DNS server to you. So that query will be sent to your local DNS server, which is actually called as a recursive DNS server. Right? So the IP address for this domain name, we are sending a DNS query saying that please tell me the IP address for this particular domain. Okay, to this local DNS server, which is called recursive. Now, this recursive DNS server will do what? It is because the DNS is very vast, very big, and it doesn't have the IP address of this. Suppose then what will do? The local DNS server or recursive DNS server will send a DNS query to the root DNS server. It is called dot. Okay, it will be sent to the root DNS servers, and you see that we have around 13 root DNS servers across the globe, 13, and the replica are also there. For example, A root server. So 13 means what? A to M. right? A root server, B and C till M. So for each the root server, we have multiple replicas across the world. So in India also we have around 8 replicas, 8 to 10 replicas what we have here. So the recursive DNS server will send a query to root DNS server. Now root DNS server will reply back saying that I don't know about www.cdat.in, but I know who can you go and contact and ask, right? So it will reply saying that you can please ask in domain name server. Because in the URL, what I am asking in is present. Root one will know about TLD, top level domain. In is what? It's called TLD, right? Now what is happening in the DNS server of in domain, we got to know, this recursive server we got to know. Now what recursive server do? It will send a DNS query to the in DNS server. This is for authoritative DNS server for in domain, in TLD. Now again, in TLD will say that I really don't know the IP address of www.cdat.in, but I can tell you, you can go and ask one DNS called cdat.in, right? Because I know cdat.in. Please go and ask cdat.in. So it will give a reply back to recursive DNS server saying that please go and ask to cdat.in, and this is the IP address for cdat.in's DNS server. Again, the recursive server will send a query to cdat.in DNS server asking the IP address for www.cdat.in, and in turn, finally, cdat.in has the IP address for this DNS server will have the IP address for www.cdat.in and will be providing to recursive DNS server. Now, what does this recursive DNS server do? Each recursive DNS server will have something called DNS cache, right? Every local DNS server will have something called DNS cache. So this recursive server will put this entry into the cache saying that for www.cdat.in, this is the IP address, right? Now it has been cached here, and the same entry from the cache will be given back to the client, and client will get to know the IP address for cdat.in, and client will be able to browse that particular website. So this is how the DNS works. And in this DNS ecosystem, now we got to know that we have something called recursive DNS server. So there can be attack on recursive DNS server. We have something called root DNS server. So there can be attack on root DNS servers. Then you have something called authoritative DNS servers. So with cdat.in and all, these are nothing, these are authoritative DNS servers. So we may have attack on authoritative DNS servers. And finally, you have something called DNS client. An attack can be there on the client also, right? So let us go back to the slides here. Yeah. So as I mentioned earlier, we have two categories of attacks. Number one category, if you talk about DNS attacks, number one category is what? Attacks onto the DNS infrastructure. So you are attacking directly onto DNS, attacking onto the root, attacking onto the recursive server, attacking onto the authoritative DNS servers. Yes, please. Yeah, tell me.
It's like a partial match, that's what I am searching.
No, ma'am. See, what is happening here? I am asking for cdat.in, www.cdat.in, right? It will be sending first to your recursive server. The client will send to the recursive server. Recursive server will send query to the root. Root will reply with the TLD DNS server, which is nothing in here in that case. Then again, recursive server is going to in. Now, in will have a lot of records inside that cdat.in, ac.in, google.in, right? And like other organizations like .daily. So all those records are there with TLD. Now TLD will say that you are asking about www.cdat.in. cdat.in somewhere is mentioned. So it will say that you can go and ask for now cdat.in. You cannot go ac.in. Right? You will go to cdat.in and then I will give you the reply. So I hope this is clear.
May I ask, so how long it will store the cache? I mean, talking about recursive resolve.
How you configure, sir? How you configure? In the configuration is mentioned that you can store cache for say 1 day, for 1 hour, for this is how you configure in DNS configuration.
Okay, so what is the recommended frequency to update the cache?
It depends on the organization. For example, I'll say that my cache entry should be more than say 1 day. Okay, so it depends on the organization. how long we can? 1 week you can store.
Okay.
Okay, let us continue now. So first category of attack is attacks onto the DNS infrastructure. So as I told you, attacks onto the root, attacks to the recursive servers, attacks to the authoritative DNS servers, and so on. So these are some of the list of attacks that I mentioned here, which we'll discuss now. So this diagram, if you see, we have one more category, attacks exploiting DNS infrastructure, that we'll see later. So if you talk about this diagram, this says that these are the list of attacks which can be there onto the DNS servers or onto the DNS ecosystem, where you have a root, where you have TLD, where you have authoritative DNS servers, your client and recursive servers, and so on. So you have an attack on the client, which is called DNS ID spoofing. We'll discuss this. Then you have MITM, man in the middle attack, which can be on the client. And then on the recursive server, you may have attacks, which is called cache poisoning attack. Because as I told you, the recursive server will have some cache. NX domain is one more attack which can be there on recursive server, right? Even the DOS, DDoS attacks can be there on entire ecosystems. It can be there on recursive server, it can be there on master, slave, or root, and so on, right? And if you talk about this master and slave DNS servers, so you know what is master, what is slave. So we are having redundancy in case one of the server fails, second server will actually serve the people. So in that case, we have master and slave. So slave will have a copy of the master, right? Now, there can be an attack on say master. Some people will spoof as a slave and download the zone data, or you can say database of the DNS servers, right? So that kind of attack is there. Again, you can have something called spoof updates, dynamic updates. I can update the entry of the DNS records dynamically, and then that can be spoofed, right? The IP address of that can be spoofed, and so on. So these are the list of attacks. Let us start discuss one by one. Now, first attack here, if you see, it is MITM, man in the middle attack, which is very much doable in LAN environment, right? So in this case, what is happening here? Because you are having one host here. This host or client wants to know the IP address of www.crat.in. Now it will send a DNS query to the recursive DNS server. Suppose this is what is the recursive DNS server. Now what is happening in between MITM attack? The person will reply on behalf of recursive DNS server, right? The person will reply on behalf of the recursive DNS server saying that I am the recursive DNS server and this is the entry, this is the IP address for www.crat.in. It is taken. The host will take and it will be redirected to some malicious website, because this MITM, this person is giving the wrong IP address, not the correct IP address, right? So this is one of the attacks which can happen in LAN environment. When a actual DNS server will reply, that will be discarded by the host, right? Or if it is MITM attack in between, because all the communication is happening through one attacker, that attacker may drop that reply which is coming from the DNS server. Okay. Now, second attack if we talk about is DNS ID spoofing. This will be applicable to the DNS clients. Okay, so you are the DNS clients, right? So this can be applicable to you all. Now, what is happening here in this case? The client will send a DNS query to a recursive DNS server, right? And you know that if you are using any DNS query, the query ID will be attached to that query. A uniquely identified query ID will be attached to each query, right? Suppose from your system 4 or 5 DNS queries has been sent. The DNS server should know, or the reply should know that, okay, this reply is for this particular query. So that's why to uniquely identify the query, if we have a query ID, a 16-bit query ID is there. Now, what is happening? The attacker will be able to get the query ID. If suppose in between attacker will see that, okay, you are sending a DNS query and this is the query ID, and it will be going to DNS server. This query ID, it will take and reply to the host saying that this is your reply. This is the IP address of your www.crat.in. So with this query ID, it will reply the same query ID. So the challenge of the attacker is what we should know what is the query ID which client has sent. Okay, so there are methods using that they can get to know the query ID. Now, I told you that you can connect this now. Change there, huh? Is it changed there? You connect it there, huh? This particular cable. See what has happened, I joined remotely, so I have the system because I had to show you a demo. So from that system, the presentation was shown, so it was a little delay. So what I do, I directly I will put here on the screen. I hope it's not clear. Sorry. Back. Now it's fast here, right? Yes, so we were discussing about IDs moving, that is done. Now let us discuss about DNS cache poisoning. Now, as I told you, this attack will be applicable to only recursive resolvers. So you have recursive resolver which will cache your replay which is coming from a root or authoritative DNS server. It will cache always. Now, what is happening in this cache poisoning attack? The attacker what it does, it want to actually poison the cache of the recursive server. Some fake record the person has to put here, the attacker has to put here. So how he will do? He will send a DNS query to the recursive DNS server. Okay, saying that I want to know the IPs for subdomain name. Here we are mentioning www.cdf.in. Now, what is happening? This recursive server will try to look up this. Suppose it is not in the cache. Suppose it is not there, the cache is empty, or this entry is not there in the cache. Now, what is happening? This recursive server will query to root first, as we have seen earlier. Then it will contact to cdf.in, and then it will contact to in and then cdf.in, and so on. But meanwhile, what this attacker will do? Attacker will reply to this DNS server saying that I am the authoritative DNS server for cdf.in, and this is your reply. I am the authoritative DNS server for cdf.in, and this is your reply. So this recursive server will actually try to get that reply and cache that reply. The fake reply will be caching here on to its cache. So next subsequent request is actually coming from the cache only. So your internal, suppose you have some local DNS server which is serving your all the clients. For all those clients, for this particular domain name, it will be leading to some malicious website. Okay. So this is nothing, it's a cache poisoning attack. How to mitigate this attack, cache poisoning? If DNSSEC is applied, this attack is not applicable. Right? If DNSSEC is applied to this cdf.in domain, then this attack will not be applicable. Okay. And then we have one more attack on to the recursive DNS server. And this attack says that annex domain. Now, what do we mean by annex domain? For example, suppose if you are saying that you have one client. So you have one client here. And this client is connecting to this DNS server. This DNS server will have some cache. It will try to look for the record through root and the hierarchy, and then it store in the cache. Right? Suppose the client is asking one domain name which is not existing. Suppose some domain name it is asking which is not there in the world, right? Now what is happening? Again, for that domain name, suppose that is abc.abc something. For this domain, what is happening? The recursive server will try to get, and it will say that this domain is not there, and then recursive server will put this entry as annex domain in the cache. So in the cache, what it put? It say that abc.abc is not there. It is not there in the world. So this entry it will put in the cache so that in the subsequent someone else is asking for abc.abc, the same reply will be given back to the client. Right? But this can be targeted by the attacker. How it can be targeted? Now let us take one simple example here, which is mentioned in this slide. Now you see that I have the attacker's machine, and you see that attacker is keep sending the domain name which is not existing in the world. Suppose abcdef1.com, abcdef2.com, and so on. It is keep sending the queries to your recursive DNS server. Now, what is happening to your recursive DNS server? It will go to root and DNS in the hierarchy. It will get to know that that particular domain is not existing. So, it will put one entry here for all those domains. So, what is happening here? Your cache is actually getting filled. The DNS cache is getting filled with unwanted data. Right? The cache is getting filled with what? unwanted data. So suppose their cache size is of say 100 MB, and what attacker can do, attacker will send huge number of those DNS queries so that this entire 100 MB can be occupied. So once it is occupied, the caching will not happen. DNS may malfunction. Right? DNS server may malfunction, or it will be responding too slow. So this is a kind of DOS, denial of service attack onto the DNS server using something called NX domain attack. So I hope this is clear to you all.
So can we remove the particular entry from a cache at a particular moment if we wish to do so?
So we have seen the attacks on to the client, we have seen the attacks on the recursive server. Then attacks can be there on the root and authenticated DNS servers. So these are the attacks, DOS and DDoS attack, which we all know. What is DOS? Denial of service. A client or the attacker will send a huge numbers of queries to your DNS server. Okay, so what is happening? Those queries, if they are more, the legitimate user will actually feel some delay in the response because the DNS server will try to resolve the query which is sent by the attacker. Right? So there is a slow response, but this attack can be sophisticated now using DDoS. So attacker will have the control machines here with him. Right? Now what attacker is doing? Sending one DNS queries to this zombie machine, and this in turn this zombie machine will send all those queries to actually your DNS servers. Now this DNS server, which is recursive or root or any other authoritative DNS server, will feel that he is getting huge number of traffic from different say IP addresses or genuine IP addresses, which is under control of the attacker. Right? Now what is happening? Within no time, this entire bandwidth of this recursive DNS server or the any authoritative DNS server will be choked, and the genuine legitimate user will not be able to get the reply from the DNS server. So these kind of attacks are nothing is DOS attack, denial of service attack. Okay, so first category we have seen. First category is what? Attacks onto the DNS servers. So we have attacks onto the clients, attacks to the say recursive and then root and so on. Now, second category says that you are using DNS infrastructure to attack others. So this is called attacks exploiting DNS infrastructure. So we have a list of numbers of attack. I discuss one by one. Now, first attack is what is called DNS reflection and DNS amplification. Now, what do you mean by this and how it happens? Now, reflection means what? Suppose we have one recursive DNS server, right, which is there in the world, and attacker will send one DNS query. So what should happen? Reply should come to attacker only, right? So if I am sending query, I will get the reply. But what attacker will do? Attacker will spoof the IP address of any victim. Any victim in the world. It will spoof the IP address saying that I am this target and this is my query. Okay. Now what is happening? Once this is coming to DNS server will resolve that query and reply will not come back to attacker because the IP address was spoofed in the query. Reply will actually go to the target. And target will get the unwanted traffic, which target was not looking for. Unnecessary traffic it got. So this is nothing, it's a phenomenon of reflection. So what attacker has to do? Only spoof the IP address of any target. Now this can be more sophisticated here if the attacker will use something called send me the response for all the records of some domain name. For example, Google.com. Google.com has a multiple subdomains, multiple records. So if I want to know all the records for Google.com in single query, the response will be bigger. Right? Earlier I was saying that I want to know the IP address for cdac.in. But here I say, give me the all records of Google.com. So Google.com may have say 200, 300 records. The reply will be so big here. So if the query is 1 byte, reply can be of 100 bytes. So this is the phenomenon of amplification. The reply is amplified here, right? So this is nothing, it's called DNS amplification attack, which will use the phenomenon of reflection. So I hope this is clear to you all. I'll show you one demo later of this reflection, but this is clear to you all, right? And how to mitigate? Can you tell me how to mitigate this? You cannot mitigate. This amplification attack cannot be mitigated. It cannot mitigate it. So we'll see the one demo here, that time we'll get to know. Now, third or second category of this attacks exploiting DNS infrastructure is called DNS tunneling attack. And it's a very dangerous attack. Means we don't have any solution which will say that you can mitigate the DNS tunneling attack. So I'll take a typical example here. To understand this DNS tunneling attack, let us take one typical example. Okay, so this camera you can turn here on the screen. Now, if I go to the online participants, my screen is visible, the TV is visible, where I am just writing something to discuss this DNS tunneling. Now, what is this DNS tunneling? I'll take a typical example here. We have a BSF border because we have armed forces because now they are saying that their network is very much protected. They are claiming that. And how they are saying? They'll say that, okay, they have one local area network, LAN. Okay, they have a local area network where all their clients are connected, the systems are connected. These are the systems of LAN. And from this LAN, suppose one internet router is there between one firewall is running. So this is nothing, it's a firewall. And in the firewall, it's mentioned that you don't allow any traffic from your LAN. Nowhere. This is the typical scenario of organization, right? You say you have firewall, LAN will not be able to communicate to the internet world. So this is the internet world. Right? Now what is happening? You will say that this is one client here. Okay. Now in DNS tunneling attack, what will happen? Even though you are having firewall here, even though firewall is here, the attacker can get the information about this client. This can download any client file from the client, right? Or attacker can do CNC or C2C, command and control, means remotely access this client. Attacker remotely access this client using something called DNS tunneling attack. So how it will do, what it will do, let us just discuss here. Now suppose I have one DNS server which is running here in the world, somewhere in the world on the internet. So this is something called abc.com. This is the DNS server which is running somewhere on the internet, right? Which is under control of the hacker. Right? Which is under control of the hacker. Now hacker has to do what? He has to install here one malware. His task is what? He has to just install one malware. It is called DNS tunneling malware. So suppose if that malware is here, and suppose that malware is running here. Now, even though on the firewall you say deny all traffic, but sometimes you say that here suppose one system is there, only this system is having internet access. Right? Internet access, if this system is having, then for this you will allow the internet, right? But for all others you will drop it. For this person you will allow the internet. Or you will say that, okay, I will allow DNS queries only. Here all the system can send DNS queries. If this is the scenario of we're going to see. All the systems can send DNS query, but they cannot browse internet. Other people cannot access this system because these systems are part of that. They don't have the public IP address. Even though if you don't have public IP address, attacker can do CNC, can take your system report, he can access your system report. So how it will do? So suppose here one malware is running on one of the client. It's a DNS malware. And this malware will do what? It will say that I want to connect to abc.com. So what is happening? It will go to this firewall. Firewall will say that DNS queries are allowed. People can do DNS queries. So it will be allowed here, then that particular malware will be able to send DNS query to abc.com. Let's perfectly all right, right? And suppose I have a file here, XYZ, and the file content is what? It's a confidential file, and content is what? Suppose it's a password of your all organization, say, big database server or whatever, some password, confidential passwords are there, 1, 2, 3, 4, then 5, 6, 7, 8. So see, these are list of passwords. So this is one of the confidential password file. Now hacker can exfiltrate this file to the attacker's machine. How it will do? Now, if the malware is running here, what this malware do? This malware will say that, tell me the IP address of 1234.abc.com. This query will be sent to the DNS server through firewall. So through firewall, this query will be sent there. Now, query will be received here. No, sorry. So what is happening here? 123 has come up to here. 123.abc.com. Means one password has come here.
The
Right?
screen
One
is not
confidential
visible.
file been opened by
Sir?
malware, and they have typed the first line and they added to that query, and that query is being sent here. Now this person got 1, 2, 3, 4. Then it
The
will
screen
replace
screen
okay,
is not visible. Hello, sir. Screen is not visible.
Now again, what it will do? It will take the second
Hello,
line,
hello.
append it to the query 5678.abc.com. The same thing will be allowed here in the firewall. It will be allowed in firewall and it will be sent to here. Now the attacker got one more line of that. So likewise, entire file can be exfiltrated to the attacker's machine. Very, very dangerous. Right? Even though you are saying that you are protected here, nobody can download, nobody can upload, but I can upload a file from this system to the other system using simple DNS queries and responses. Process will be so slow. Suppose here this file of say 1 MB, 1 MB may take say half an hour. But your confidential file can be exfiltrated to the attack machine in that half an hour. So this is the phenomena, this is the concept of DNS tunneling. You are tunneling the other traffic inside the DNS queries and responses. This is the meaning of tunneling. You are carrying other traffic. So what traffic I am carrying? I am not carrying any traffic. So I am just uploading the file. So FTP server. So FTP server is running inside the DNS server. It is used inside the DNS server.
अगर DNS उसके भी हो सकता है क्या?
अभी हम DNS की बात कर रहे हैं सर, तो DNS से तो हो सकता है definitely. I'll show you one demo also. The demo is ready, right? I'll show you the demo also. DNS से तो हो सकता है. DNS के बगैर अभी देखना पड़ेगा कुछ और मैं करेंगे, right? So I hope this is clear to you all. This is clear, right? Okay, I'll show you a quick demo on this DNS tunneling attack. Then we'll again see a demo on DNS amplification attack. Switching it. Okay, so what I have is two systems here. If I open MS Paint here, so that online people also can see. So I'll be having two systems here. This is one system, okay, and this is the second system. This second system is nothing, is one DNS server, right? It is a DNS server which is under control of attacker. Right now, this first system is a system, normal system, which will send the DNS queries, right? Which will send the DNS queries. Now, in between, there is a firewall which is there, and in this firewall, it is mentioned that deny all. Deny all. Before that, it is mentioned that allow DNS queries. Allow DNS queries and deny all. So what is the meaning of this? All other traffic will be denied. Only DNS queries are allowed. Only DNS queries are allowed. Other things will be denied. Now, in this case, what is happening? On this client machine or any system attack or target system, we'll say this is target system. This is the target system. So on this target system, I'll be running one malware called DNS cat 2. So this is the malware which I am running on target system. Okay, and this DNS server which is under control of attacker is also running DNS cat2 service. This is the service, that is the malware. Right? And then what I will do, I will try to, here I will be having one file. Suppose abc.txt file is there. This file we will create it on the client. And this file can be downloaded to this machine using this particular setup. So this setup is clear to you all. So we say that we have one system where one malware is installed, this is called DNS cat2. Then we have one server which is under control of the attacker, where the DNS cat2 is running, a service is running, and in between a firewall is there, which will block all the traffic, only allow DNS queries. Right? So this is the setup. Now for this setup, I'll tell you this is my DNS client here. So DNS server, let us be say this is the attacker's machine. So this is the attacker's machine. On this attacker machine, DNS cat2 service is running. And if you see this IP address of this attacker's machine is 4.102 is the IP address of attacker's machine. Okay, and then I have one system where this malware is running, DNS cat malware. Okay, so here you see this is the IP address of say client machine. The same thing we'll try to put it here on this page here. So the IP address of this is 192.168.4.101 and the IP address of this is 192.168.4.102. Okay, this is the IP address. And currently let us see on the client what firewall is running. So on this client machine, if you see, I'll say IP tables minus NL. No firewall is there currently. No firewall, right? It says accept. Means it's IP tables firewall which says that currently everything is accepted. So if it is accepted, then I can ping 192.168.4.102 is the attacker machine. I can ping, right? So you see that I am able to ping. Done? Okay. Even if you see here, I can on the client only, I'll be able to browse internet. So this is the internet which is accessible on the client. Now what I want this setup. So in that, I have disabled everything onto the client. This, I have to say, this firewall, I'll say disable all, allow only DNS queries. So how do I disable all? I'll add some firewall rules inside that. So I will add one firewall rules. I'll say IP tables input drop incoming connection. Drop all the incoming connection. Again, I'll say IP tables policy output. I'll say drop. Outgoing connection also please drop. Okay. So both incoming and outgoing connection I have dropped it. So if I am dropping it, now I say if I want to ping that IP address, will it allow me? No. No. So you see that ping is denied. Means firewall is active. Firewall is active. Same thing if I try to browse also, it will say I will not be able to browse now. Why? Because my firewall is dropping all the packets, outgoing and incoming. See, it is not going. It's just rotating, trying to connect to the Google website. Okay. So now this client is at the safer side. And this is what is there in our BSF. Suppose let us take the example of BSF. This is there in the BSF. Now on the firewall, you have done some configuration saying that allow only DNS. Now let me allow DNS. I have dropped on. I'll allow only DNS. So DNS outgoing and incoming I'll allow. Right? The DNS query outgoing and incoming DNS queries I'll allow. So let us do that on the client. Again, if I go back to the client here, I'll say IP tables append, right? Input minus P UDP. DNS uses UDP, right? Minus, so I'll say output. So before that, I'll show you before applying this rules, I'll say incoming outgoing is dropped. I will try to do DNS queries. NS lookup is what? It will send a DNS query to some DNS server. So I'll try to send to a DNS our main DNS server, one query I am sending. Will it allow now? It will not allow because incoming, outgoing, everything is blocked. So it will say, I am not able to send a DNS query to google.com. You see, it is doing only, it will not allow you to send the query. Right? Let's keep connecting and somewhere it will show that it is not allowed. Okay, so currently it is not allowed. If I want to allow, you see, no DNS server to this is the reply which I got it. Now I will add a firewall rule in IP tables. I'll say for outgoing connection, DNS you allow. Right? Outgoing connection, DNS you allow. So I'll say IP tables minus A output. Then I will say minus P UDP, DNS uses UDP, and then say minus D port 53. So DNS will use UDP port number 53. So outgoing port number 53 is allowed now, minus J accept. So this is one rule I added here, which says that outgoing DNS query will be allowed. I'll say enter. So this rule is added. Now again, if I see my IP tables here, so sorry. You see that one rule is added, outgoing. So if I send a DNS query, I'll get a response. Suppose if I'm sending a DNS query, I should get a response, but response incoming it is by default drop. So incoming DNS also should be allowed in this case. The response should be allowed, right? So what I will do here, again I'll add one more rule here. IP tables, append in input, I'll say, and minus P UDP minus S port 53 minus J accept. If anybody is giving me the reply from port number 53, please accept. DNS reply if I'm getting, please accept. So these two rules I added, only related to DNS, right? If I say again IP tables minus NL, you see these two rules only are there. These two rules are only there. Okay, one outgoing DNS, incoming DNS. And now, still I'll see whether I'll be able to ping that system or not. 4.102, the other side, I try to ping that DNS server. See, ping is not allowed. But if I say NS lookup www.google.com, you see that I am getting DNS responses. Right? So this setup which I wanted, it is now there with me. This setup which I wanted is there with me. So in this system, I am having this firewall which is running and outgoing everything is denied, only DNS queries are allowed. Okay. Now, if this is the setup, what can I do now? So here, I am already running one DNS cat service onto the attacker's machine. So this is the DNS cat service which is running here currently onto the attacker's machine. This is DNS cat service. And then onto the client side, I have to execute that malware. So at the client side, this side, I have to execute this malware, DNS cat to malware. So if it execute from here to here, communication can happen through DNS queries and responses. So let us now execute that malware on the client side. So how do I execute that malware? I will just say that /DNS cat minus DNS server is equal to 192.168.2.4.102 port 53. So this is the command which I executed here. What it says that this is the malware which is trying to connect to that DNS server over port number 53. And it will connect. Why? Because DNS queries are allowed. Okay, if I say enter, 1 minute. Here is equal to was missing. Sorry. The is equal to was missing. Now you see that it is connected. Session established. Means what? I can actually do whatever I want between this server and this client. Means this is the attacker's machine, this is the client. One session through DNS tunneling is established. Now what I will do, I will have one file here, abc.txt, which I want to exfiltrate to this particular system. I have a file called abc.txt. So let us create this file here on the client machine. So one session is established, and then I will create one file abc.txt, or any file name will say, right? We'll say, sir, what's your name? Huh? FAYZ.txt. This is the file name. Okay. Hello, this is for demo, right? This is very confidential file. Okay, this is what I am writing in that particular file. So this may be the confidential file, which is sitting where at the client side, where that malware is running. Now, from the server side, I am now sitting on the server. Session is established. I see here there is one session which is there. So I am sitting now on the attacker's machine. I want to remotely control that machine, right? So I am sitting now at attacker's machine. This is the attacker's machine. I am saying that one session is established. One number one is one session. So I use this session. Now I am into that session. Okay, I am into that session. Now if you see, I can do what? These many things I can do. I can download a file. So I say download. What was the file name? So I don't know what is the file name. Suppose attacker don't know the file name. What attacker will do? Attacker will open a shell between my system, attacker system, to the client, the compromised client. A shell will be created, remote shell. So I'll execute this command shell. Right now, here one more shell session is created. I'll say I'll use this shell session. Right, this is shell session. I'll say ls. ls command is giving me the output. And here pr.txt is one file. I got to know this is the confidential file. ls command which I am executing here on the on attacker's machine, which is getting executed there at the client, output is given back to me. So entire shell is with me, CNC or C2C, command and control. I can control that particular system. So I got to know what? I got to know the file name. If I want to see the content, I can see the content also. So see, this is the content of that file. Where I am seeing on the attacker's machine. Even though firewall is there, you see firewall, it says DNS all. So I am talking about, sir, BSF. If you say that this is your entire network is private network, no internet is there, but still somewhere router is there, and on that router somewhere you are written in the firewall that allow DNS queries. Still people will be able to access your system remotely. Very, very dangerous. Right? Now, okay, let me download this file, abc.txt. Okay, so how do we download here? I got to know the file name, pr.txt. And then what I will do, I'll exit from this shell and again let me download. So this shell is exited. Again, I will say window -i1, and then I'll say download as YA. Right? What was the name? I am typing this command onto the server, means attacker's machine only. Now you see the file will be getting downloaded. See, wrote 55 bytes. So I'll go to server here and I see whether that file I got or not. You see fires.text I got text dot I got it. So I say cat fires.text. I see the same content of the file I got it given. Even though I have a firewall, the file can be data can be exfiltrated from one system to other system. And even entire command and control means your system can be remotely accessible by the user. What attacker has to do? Somehow he has to push one malware to your machine. So आपके DIG बैठते हैं वहां पे, उनका सिस्टम बोलते बहुत प्रोटेक्टेड है, पर उसमें आप देखते हो कि दो नेटवर्क आते हैं उसमें, एक लैन में जाता है, एक इंटरनेट पे भी जाता है, तो उसमें ऐसा हो सकता है, they can do that. Now what this is clear, right? What is DNS tunneling? How it can be done? Very easily it can be done. The only challenge for the attacker is to drop a malware to the target machine. If he is successfully able to draw, even though firewall is there, even though you have UTM and all, still this attack will not be detected. Still this attack will not be able to detect it. Right? So let us move back to slides here. So I hope this particular attack is clear to you all. DNS tunneling attack. Any question here? No question. It's clear. How to mitigate? This is the biggest question.
Firewall can be changed.
What you will do change? DNS should not be query should not be allowed in case if you are having the separate. But if you see normal IT network, always they want internet. Normal IT network, always you allow DNS queries, right? So in that case, you cannot mitigate this. In that case, you will not mitigate this. With IT network, you have to allow DNS queries. Then only your internet will be browsable. Otherwise, you will not be able to browse. So there you cannot mitigate. But in your isolated network, disable DNS, then it cannot be.
How are the domain names? What kind of domain names get connected to the CNC in this case?
Any domain name. Any domain name. That's what attacker will have a domain name called abc.com, which is the genuine, which is what genuine, right? So I have created for that setup also, internet setup also, where I have used a domain called coe.dnssecurity.in, your website name. I use that domain name for DNS domain. And from outside, I can exfiltrate the files to that particular server, where the DNS server is running, DNS cat is running. So for this attack, we have a lot of tools. I'll just tell you those good names. These are the tools. We have just seen DNS cat 2. We have iodine. One of the best tool for DNS tunneling is iodine. Right? Then DNS cat 2 also is there. Then DNS 2 TCP, Ozyman DNS. There are so many tools are there. So my research work was this only: how to detect this DNS tunneling. So somehow I achieved something. I said that if you are using iodine, this is the method. If you are using DNS cat 2, this is the method. If you are using DNS 2 TCP, this is the method. So I have developed the tool specific IDS signature. In my research work, tool specific IDS signature I have developed. And I said that I have at least almost 10 tools. For those 10 tools, I have successfully developed the IDS signatures, and those IDS signatures will be able to identify if you are using DNS cat 2. It's a this is tunneling attack through cat 2, which is happening now, right? But if you have a new tool, then still you don't have any solution. So again, one signature you do. Okay, so I'll give you one more example here. I hope we have time, Gopi. Good time. Yes.
There are malwares you have antivirus and malware protector.
You might have seen this malware is only sending DNS queries. It is not led to some antivirus signature, which is slowing your system or which is trying to get some data and all. It will only access your storage. That's all. Yes. So here this malware will do what? It will send the DNS queries. So read your file and send there.
It is based on DNS.
Yeah, definitely. Okay, so one more attack. So this is the second category. Attack exploiting DNS infrastructures. So in that DNS tunneling attack you see, we have one more attack called DNS reflection, which I showed you earlier. This is DNS reflection. So let us try to demonstrate how this DNS reflection can be done on LAN environment. It can be done on WAN also. LAN. So in LAN, what I do? I will be having a DNS server running somewhere onto the internet. Okay. And I will spoof the IP address of one of your systems and send the DNS query to the internet DNS server. Now reply will go to you, and you will see in your Wireshark or TCP dump that one unwanted reply is coming to you. So I can amplify also here. I'll ask for google.com all the records. You will be getting. I will be sending a 1 byte query. You will be getting 100 bytes reply, big reply, 100 times bigger. Right? So that we can see. Now I'll show you the demo now, DNS amplification attack. Again, for this, what I have, this is what I am having. It's called DNS-DRDOS.c. It's a file which is available on internet. It is for DNS amplification attack, DNS-DRDOS.c. I'll just show you on internet at GitHub. This will be available. I say DNS-DRDOS.c GitHub. So this file is available. It's a simple C file. It's a C program. Okay. So you can see this is the program here. And if you see this program, how to minimize it, how to minimize this. I have to open that tab. Yeah, open here only. And you see, this is the program. It's, I guess, some 200-300 line program. Okay, this is 500 line program, right? 660. So this is the program which I'm going to use here. So this program already I downloaded on one of my system. This is the system where this program I downloaded, and I compiled that program. Okay, you see, program is you have to compile it. I compiled it. So once I compiled, you see that I got one say output object file, right? Executable file. It's an executable file, right? So now if I want to execute this file, what I'll say, this is the help it will show how to execute this command. Now to understand this amplification, what I will do here, I will open one more page. Now here I'll say that I'll be having one list with me, right? This is the DNS server list. So you have public DNS servers 8.8.8.8. It's a public DNS server. Sir, NIC has one DNS server. 10.10.10. This is NIC's DNS server. Huh? Open DNS. Good, sir. So these two DNS I am using. And we have 4.4.4. here. And here even we have our own DNS server. What is the IP here? Huh? Okay. What is the IP you don't know? What is it? 120, 120 I know. The starting to IP system. Okay, leave it. You tell me later. So these are the list of DNS server the attacker should has. Right? Attacker is having. And attacker has this machine where this DNS DRDOS program is running. Okay? And then we have one target. So this is the target machine. So suppose target machine IP address is, suppose I write the IP address of say my own machine. So I'll see what is the IP address of my machine here. If I see, I'll get to know. I can use here also, no issue at all. But to show them how it's working, I'll use mine. 4.103 is my machine, means my Windows machine. It's a Windows machine. So I'll write this 192.168.4.103. Okay, and this attacker's machine IP address is 192.168.4.102 or whatever. Okay, now what is happening? I should have this list of DNS servers. The query will be scanned to these DNS servers, right? Spoofing the IP address of visiting machine. So from this system using DNS DRDOS.c, the query will be sent here, but this reply from them will come to the target machine. Right? And target will get the unwanted traffic. So this is the setup which I'm going to achieve. Okay. So I have this machine with me where DNS here DOS.c is there with me. I just open that machine, and in that machine only I have the list of the DNS server. I'll say list dot text. So in that I will say a dot. This is plain. No, I want server. This. Yeah. So here, if I say one list I'll create, I have written a.a.a.a.8, 1.10.10.10. Okay, this 2 IP address I mentioned, and I'm saving it. Okay, this is available with the attacker system, and in the attacker system, I'll say DOS attack help if I see, and then I'll say DOS attack minus f. This is the file. Okay, and then I will say minus s, I guess, spoof the IP address. Which IP address I have to spoof? 192.168 and then 4.103. Just let me confirm here the same IP address on the system. Yeah, correct. And then I'll use the domain name the google.com and loop this query for 1010. Means 1000 request will be sent to a.a.a.a and 1.10.10.10. The reply will go to the Windows machine from 8.8.8.8 and 1.10.10. So those 1000 replies will come here. So if I will check here, I'll open on my system Wireshark. Okay, so I want to check on my machine where the Windows target machine, Wireshark I open and see what DNS traffic is going there. Okay, so I'll use Ethernet device, the Ethernet, and I'll just filter for DNS only. Okay, and you see what is happening. If I send this command here, it is sending queries, reply will come to CD. 1.10.10.10 is replying to that machine. So this is the reflection which is happening. Amplified reflection. So like that, any internet resources can be targeted. Right? So if you're having any internet resources, their unwanted traffic will come from the DNS servers. But your firewall will see it's a reply, it's simple reply, it will allow. Your firewall will allow, right? And then there may be a denial of service attack on your network. Because your network can be choked with this kind of unwanted traffic. Right? So this is clear, DNS amplification attack. Is it clear? Any question, any query? Okay, so let us go back to slides. No queries are there. Yeah. That's what mitigation will look at now. That's a big question mark. It's a big question mark, obviously. Obviously, some people say that some security industry, they say that we have solution which is called DNS firewall. DNS firewall secure DNS they are protecting their say organization using this particular appliance or device, right? But that is not a foolproof. If I will have one small say malware which will only send very small DNS queries to the DNS servers, reading your data and sending very slow, that the guy will not be able to detect. Right? So normally this kind of DNS cat and all, they will take 1 hour for 1 MB file to download or 1 GB file 2 hours. But in that case, I'll say full 1 day I'll take for 1 MB file. Very slowly I'll do. I'll wait again, I'll copy, wait, copy. Still it will be exfiltrated. They will not be able to detect. They will not be able to detect at all.
People who are running a complicated domain, like organization having their own DNS server, and resolving the domain outside. It's a big risk for everyone on this.
The appliances are there, DDoS appliances like DOS attack. If you have more traffic which is coming, they will say that you block those traffic. From same IP, more traffic is coming. But sir, okay, so this is all about this session. Hijacking is nothing. Any client can be targeted to this particular attack called DNS hijacking. In hijacking, what they will do, they will install a malware on the target machine, like clients, normal clients like your system. And what that malware will do, it will only change the TCP/IP settings of your computer system, and they will change your DNS to their DNS. Right? So your DNS will be your ISP DNS, or you might be using 8.8.8 or 1.10.10.8. They will change it and they will write their DNS entry there, and you will be misleading to some malicious websites. So this is called hijacking, DNS hijacking. So there are so many malwares which are there which will change the TCP/IP settings. So this is all about this session. What is written here? A successful DNS system is like oxygen. Everyone takes it for granted until it disappears. So this is what is the mock practice is telling, that you should secure your DNS infrastructure and you should keep monitoring your DNS infrastructure. Thank you very much. Any question? Thank you, sir. Thank you, sir. Any questions? Online participants, any questions? Let's check chats. Stop sharing. So how to host a local DNS server? Someone is asking how to host a local DNS server. Bind you can install, and there are only few steps. You say if you're using say Linux Ubuntu, you say apt get install bind. That's all. Story is over. You will install. If you're using CentOS, you say dnf or yum install bind. Done. You have to do real configuration. We have one file called namely.conf file under etc directory that you will modify and write your IP address of your own system where the DNS service is running. That's all. Nothing else. And then how protect the email DNS attacks in many ways. I don't know what sites can we remove a particular entry from cache? Okay, one question is there. You are a DNS administrator, and you got to know that your one of the entry is fake entry. How do I remove it? Only that entry. You cannot remove that entry only, but you have to flush the cache. We have a method to flush the cache. If you restart your DNS service or reload your DNS service, not reload, restart. If you do, the cache will be cleared. Right? Or to flush a cache, we have a command in bind also. Using those commands, we can flush it. Okay, thank you, sir. Thank you, Dr. Sanjay. Yeah, so might be that I'll try to answer the question. One of the questions was, can I host a DNS server? There are two types of DNS server which we know. One is the recursive resolver and the other is the authoritative name server. So you can visit our portal, coidnssecurity.in, and we have the mechanisms. We have a manual uploaded on our portal on setting up DNS server. It's as simple as Dr. Sanjay was mentioning. So you can follow the steps in that. It's a detailed manual with screenshots available. Number one. Number two, the other question was emails. Email, right? Okay, right. Email, there are two dimensions to that. One is you receive an email, and whether that email is from a valid mail exchange server. Okay, right. Let's say that gmail.com is a valid mail exchange server. It can be gmail123@.com. Right. So in that case, the domain name from which the email has been received itself is a malicious server. Right. That is one part. The other part is that you may receive a link as a content in an email. Right. And you may click on that link in that email. Right. So that is there the DNS security comes into the picture, because you are going to click on that link, and the DNS ecosystem is going to resolve that. So there the DNS security has to be robust to report that it's a malicious link or allow whatever. Okay, to classify that. Right. So the other dimension, yeah. So thank you, Dr. Sanjay, for the informative session, and it was very enlightening. And the part is that he pretend all the internet audience. So yeah, of course, there is internet is full of vulnerabilities and threats, but there are solutions to that. May not be foolproof, agreed, but there are solutions to that. Okay, so
Thank you very much, and we'll break for lunch now. It's a 1 hour break. We'll
45 minutes, already there.
Okay, yeah, it's 45 minutes break now. So we'll return back in 45 minutes to resume the session. Thank you very much. Yeah. Good afternoon, everyone. So welcome back to the session. The next session is on DNS with Amazon Route 53. Okay, it's a cloud. DNS with Amazon Route 53 is the next session. The speaker of the next session is Mr. Ashwin Murali. Mr. Ashwin Murali is a seasoned DevOps and cloud infrastructure leader. He has scaled multiple startups from a few thousand users to millions. He has a passion for keeping systems running at all times and making infra the most boring part of engineering organization. Ashwin currently works with Autonomous Robotics Research Center at the Technology Innovation Institute in Abu Dhabi. He is responsible for managing the infrastructure and engineering that helps the team build vehicles with self-driving capabilities. Thank you, Mr. Ashwin, for joining. It's over to you.
Hey, I'm just trying to get my screen share working. I'm going to rejoin in just one moment.
Hello. Speak on them.
Hey everyone, sorry for that. Can you folks hear me clear?
Yes, please continue.
Lovely. And I'm sharing my screen. Is it working?
Yeah, it's visible. Yes, please continue.
Okay, lovely. Awesome. So let's get going quickly. This is going to be a 45-minute talk. I'll try to wrap it up in about 32 minutes so that we can take some time for questions. Because I'm fairly confident that while people are aware of DNS as a concept, there are some bits that that is not what you would expect in your traditional understanding of this tech, right? So to get started, I think the introduction sort of explained everything. My specialization. My name is Ashwin. My specialization is in scaling startup tech. My job has been with AWS as one of the primary cloud providers for the last 15 years. Although I've worked with Google and Azure and other infrastructure providers on the internet. I have scaled multiple startups. I have done data centers. I have done pure cloud native. I have also done a mix or hybrid cloud that people call. And the reason why I got introduced to Balaji and the entire CDAC community was because I was running my own email and DNS servers at some point in time, and that led to a training session, and that led to more. And it's super amazing to be able to talk to you people today. Right now with TII, I build data centers which manage the entire engineering and AI capabilities for my research division, which is the Autonomous Robotics Research
Ashwin,
Center.
we are not able to hear you.
Can you hear me now?
Yes. Yeah, you're back.
Okay, I don't know, something with the line. Okay, quick look at what we're going to be looking at today. We're going to do a quick crash course on DNS. We're going to look at DNS on the cloud, what it means when we say DNS on the cloud. We'll quickly flow into Route 53. We'll do a little bit of what special offerings Route 53 has and why cloud DNS changes things for the world. And then we look at when you deploy an application on the cloud, what are you looking at? Does someone want to take a guess on what this race car is and what it is doing here? I'll give you people like, I don't know, if you want to talk. I'm guessing the mic is open, so feel free to do that.
Anyone who wants to answer that?
Someone wants to do a random guess.
No, so you can.
All right. So if you notice this race car, it doesn't have a cockpit. This is the autonomous race car that we are building for a racing event called the Abu Dhabi Autonomous Racing League. The idea is to take a race car, make it completely self-driving, make it completely self-capable, and put it on a racetrack and race it with 10 other teams. The smaller idea is that. The bigger idea is to build systems that can respond in microseconds and milliseconds, so that tomorrow in future, we can hopefully have safer driverless cars, right? So that's a very, very quick hi, hello on that. Now, going to the main topic, history of the DNS. So do you know how DNS started? Computers weren't talking to one another when the initial computing concepts were built, right, at DARPA. So connecting two machines on a network was ridiculously expensive. So they said, when we do networking, and we call it the internet, which was initially called the internetwork, it was very simple. They had two IPs. They said IP1 can talk to IP2, IP2 can talk to IP1. Now, in the University of California research centers at Berkeley, which was where the entire internet concept started growing and DARPA started growing, the total number of computers were 100. Each computer was a room, right? So they actually had 100 rooms. And it was still easy because people used Post-its. But then the computing revolution happened, computers became famous. So people said, let's move Post-its to hosts.txt, a text file on the machine, which will help identify and recognize computers. Beyond that, we went to FTP. And you know the problem with FTP, right? One of you writes a DNS entry, I write a DNS entry, we don't know which one is a valid entry, right? So now from there, we said syncing FTP files is too cumbersome and the bandwidth requirements are too crazy and there are too many changes that are happening too frequently, right? So from there was how in 1983, 40 years to today, we had RFC 882 and RFC 883. This was what you call as DNS today, right? Where it said we will define something called a zone file. This zone file will be transmitted in binary chunks over UDP, and we will have a concept called a name server and so on and so forth. The modern DNS system that you see today is literally these four RFCs, 882, 883, 1034, and 1035. These are literally 4 text files on which the internet runs. So let's look at what the DNS protocol means for us. The DNS protocol is asynchronous, which means you send a request, you don't care. You hope that the response is there and you get a response, right? It's a very simple packet format. It's got 2 headers and the rest of it is the payload, right? DNS, you do have DNS over HTTP, you do have DNS over TCP, you do have more advanced DNS protocols, but traditional DNS in its true form is still on UDP. 90% of packet lookups, in fact, 98% of packet lookups for name to IP mapping happens only on UDP protocol. Everything is cached, right? So DNS responses specify caching objectives where you have something called a TTL field or an expiry, and that is how long the record is held in the system, and no further queries to that same request are made. Servers respond to queries with additional information, and data is indexed by domain names. We'll look at an example of how this works. Domain name is a sequence of labels. Each label is separated by a dot and is maintained as a tree, right? So you have root, a dot at the top. You have domain names as branches, and each domain name is a leaf, or a subdomain can continue to further become leaves. Administration is shared, which means there is no one who specifically owns DNS. There is no one single entity which owns DNS. Even the IETF, which defines and manages the RFCs, the cert bodies which handle IP management and all that, CERN level organizations, all of them are not entirely in charge of DNS. Now, let's look at what types of DNS servers we will encounter, and from there we will go on, right? You have something called a recursive resolver. This is the server that you will usually talk to. This server is a middleman between the laptop or a computer that you're working on and the actual name server that holds the data pertaining to a domain, right? You have something called a root name server. The root name server is literally the top level hierarchy, right? It is the first step of hostname resolution. It tries to figure out who do I need to talk to. Every computer on this planet is provisioned with a list of root name servers, right? And they keep updating themselves periodically to update the IP addresses. But here's a fun fact. There are only 13 root name servers. Do you know which ones they are? Do people, does someone want to talk about it very quickly? Like root name servers. If you're in a DNS session, you should know what a root name server is and what those 13 servers are. Do you know that? So they start from the alphabet A and go till the alphabet M. It's a.root-servers.net. That's it. And then you have a TLD name server. So a TLD stands for a top level domain, a .com, .org, .in, .edu, etc. Right? So when a request goes out to look up for a IP address for a domain, the first lookup is at the root name server. The second one is at the TLD name server. And from there goes to the authoritative server where the actual DNS records are held. And that is from where you get the IP address of this domain that you're trying to access, right? Now, DNS terminology. What are we looking at when we say DNS? We say zone file, right? A zone file is a file. It's a plain text file. Anyone can actually look at a zone file and read it directly by opening it in Notepad. And if there is a DNS workshop that you're attending at CDAC, that is one of the first sets of things that you will build when you when you work on your DNS techniques. So it's a file containing a mapping of different domain names to IP addresses. Whatever, google.com, 8.8.8.8, cloudflare.com, 1.1.1.1. So that's the kind of mapping that you get. Then you have the records, which is individual entries of a domain and an IP address. You have a TTL. You have 5 different kinds of TTL. You have a refresh TTL, you have a expiry TTL, you have a no cache TTL, and so on. And sorry, was that a question? Balaji, was that a question?
No.
Can I continue?
Yes, sir. Tell me.
Was there a question or can I continue?
No, please continue.
All right, lovely. So when you want to look up DNS records away from how a traditional browser does it, then you use the command dig, right? So digging for cdac.in, this is how dig responds. It says that my resolver asked for recursion, my resolver got recursion. I asked one question, which is who owns or what is the IP address of cdac.in? I got one answer. This answer was not an authoritative answer, which means I got it from a resolver. I didn't get it from the actual source, and I got some additional information, right? So this is what the IP address of cdac.in is. The TTL is 1200 seconds, which means the moment I get that answer, I hold it for 1200 seconds before I go and ask for another time, right? How long did the query take? The query took 714 milliseconds. Who did I talk to? I spoke to a server at 1.1.1.1, right? This is your traditional DNS, right? Now let's see how it actually dug through. The browser went to a recursive resolver. The recursive resolver went to dot, which is the root name servers. From there, it checked what the top level domain is. The top level domain wasn't a .com, was not a .net, was not a .org. It turned out to be a .in. So it went and asked the .in TLD to give it information about CDAC. So TLD said, hey, CDAC as a domain is held at point A. So it went to that server and it said, hey, I want to know the fully qualified domain name ending with www. So for www.cdac.in, you get an IP address. Again, same thing. CDAC has a mail client, which is called webmail. Again, you get another FQDN and you get an IP address for that. So far, this is a very quick crash course on DNS. Do you have questions? Because right from here is where things get confusing. I can hold for a minute before we go ahead. If there are questions and you want to ask them on chat, that's okay. If you want to ask them on Zoom, you want to just unmute and ask the question, that's fine by me as well. And people who are at CDAC, if you want to ask a question, just raise a hand and probably someone can help you with it.
Any questions?
No, sir, you may continue, please. I think we will take questions at the end of the session.
Lovely. I'm continuing. So this is the part where things get interesting, right? So now DNS is fine as long as you're running a decent sized organization. But you need a custom solution when you're running as Amazon Web Services or Google Cloud or Microsoft Azure, right? Each of these cloud providers, they run DNS, but they run it very differently. It is, what is Route 53? We're focusing only on Amazon's cloud DNS today. We're not talking about GCP. We're not talking about Azure, although you can creatively assume that the implementation details aside, this is how it will work on all three providers, right? So Route 53 is AWS's managed DNS service. Their definition says it's a highly available and scalable DNS web service. Look at the definition. It doesn't say it is a domain name system service. It says DNS web service, right? And this is exactly where the differentiation starts happening. Route 53. We should actually talk about the name as well, right? Route 53 because 53 is the port on which DNS queries are answered by RFC, right? RFC communication happens on port 53. Route because by definition, it is telling your browser which route to take to get where, right? So Route 53 connects user requests to internet applications running either on AWS or on premises. So you can use AWS DNS or AWS Route 53 to also handle DNS management for servers that you're running on your own premises. Route 53 lets you do the following. Simple, boring stuff, right? In fact, the reason why it's called simple and boring is specifically because this is the most basic things that DNS does. It lets you register a domain and it will let you manage all the DNS records for a domain. And that is the only boring stuff that it does. What Route 53 additionally does is it does private and public hosted zones. What that means is when you have services in your organization that are running on different servers, you want to expose certain services to the internet, you want to hide certain services from the internet, but you want them accessible only from inside the office. These are things that AWS can do using private and public hosted zones. Any service that has an IP in a public hosted zone will be accessible over the internet. Any service which has an IP in a private hosted zone can only be accessed inside your office premises or inside the network premises, right? What else can it do? It can do advanced routing. This is where the fun starts, right? AWS can route a user to a destination based on IP. It can route a user based on geolocation. It can route a user based on latency. And we'll look at examples for each of these in a few minutes. So DNS record types are where you start defining all of these properties and start having fun with AWS and cloud-based DNS. So you have something called a standard record type, right? Let's look at what all we get to do here. You have a standard record type default. You just have an A record, quad A record, MX record, TXT record, C names, etc. You have failover records. You have weighted records. You have geolocation records. You have latency based records. You have IP based records. You have multi-value records, and we look at each of these now. Standard. This is what you're used to when you say bind, unbound, or any other DNS server, right? There is a DNS record. There is no additional routing or features that are baked into the record. It's your traditional DNS RFC that is being delivered here. You have a client. The client wants to talk to example.com. Example.com has 2 A records. That's it, done. So when you query for example.com, you will get 2 A records as a response. It will be a traditional DNS response. Nothing changes. The fun starts here. Failover records, right? So when you say there is a failover record, what this means is you can trust AWS to look at your systems on the inside, try to check them periodically to see if they're available, and then alter the DNS response basis they are active or they're unavailable. So you have different kinds of failover routing. You have something called active passive routing, which is an active standby kind of a system, where you have 2 records at least or more. And then you have health checks. You have a primary health check on the primary system, and you have a secondary health check on the secondary system. When the health check on the primary fails, you will notice that AWS will not return the records of the primary. It will in fact return the records of the secondary, and you don't have to worry about this routing. AWS takes care of the TTLs, AWS takes care of the switchover, AWS takes care of the zone file remapping. All of this happens automatically and it happens internally. So this is an example, right? So you have 2 setup. You have a failover 1.example.com and you have failover 2.example.com. When a client hits example.com, by default, it goes to failover 1, which is your active setup. Now, let's assume you're running a deployment, or you have a server issue, or you have a downtime because you want to do some sort of maintenance, but you don't want the users to be affected by this downtime. In that scenario, what you do is you switch off the health check on the primary. A health check is a ping or a check on a service periodically to see if that system is healthy or not, that system or group of systems is healthy or not. And as long as the system keeps responding in a way that is expected, AWS will assume that the system is healthy, right? Now, once the health check starts failing, AWS then will immediately remove failover1.example.com CNAME and IP address from the DNS response. So nothing changes as far as configuration in this picture, but the client will connect to example.com and will automatically get routed to failover2. This is your active passive setup, right? You have something called an active setup. You have the same kind of scenario. You have a DNS record with 2 or more records. You have primary with health check. You have a secondary service with health check. And when the health check on the primary fails, the Route 53 ecosystem will automatically shift traffic to the secondary. When primary is back, the Route 53 ecosystem will shift traffic back to the primary, right? And it assumes both of them are up. It can keep flip-flopping between these two. The difference between what you're seeing in active versus active-passive is if active comes back up in an active-passive setup, the traffic does not flip back. But in an active setup, it automatically flips back. You have something called weighted routing. Weighted routing is something that you have seen in traditional DNS, right? You have weights for MX records, for mail server records. If you look at Google's MX, it will say weight starting from 10 to I think 50, right? So the idea is to shape traffic based on weights. The record with the lowest number is considered the heaviest record, and most traffic is sent there, right? So each traffic has a weight associated. Traffic distribution is based on relative weight, right? So it averages the weight and then sends traffic over. You add a health check. What it does is then, given 5 records with different weights, if one of the servers behind one of the records doesn't work, it immediately removes that server from service and recalculates the weights and rebalances traffic automatically, right? So if you say weight 50 for LB1 and LB2, it is actually transferring traffic. Every alternate packet is going to an alternate server, right? Next, geolocation. This is straightforward, right? What we traditionally try to achieve with BGP in the IETF namespace, Route 53 adds another layer of ease and abstraction on top of that. So you have multiple records for a domain called example.com, and each set of records is actually pointing to a different data center. AWS then takes care of relaying this IP address across all its data centers with their BGP network, and then based on where the traffic is coming from, the closest data center is where the traffic is sent to, right? Now, each record, like I said, you need to provide one default location so that if all locations are down, at least one, or if no location is mapped for a user, then at least one location is where the traffic is sent to, right? So you can do geo-targeting based on continents. You can say Asia, you can say Asia Pacific, you can say MENA, you can say LATAM, you can say Africa, you can say North America, South America, things like that. Or you can do specific countries, traffic for India. So for example, if you look at how the Aadhaar ecosystem works, you cannot operate your Aadhaar data, or you cannot work on your Aadhaar data if you're outside India, right? And this is sort of how it works. The traffic coming in, the ASIN of the client IP address is checked. if the ASIN does not belong to a particular country, that traffic packet is dropped. So this is sort of how it works, right? So you have client going to example.com, but then based on where the client is, it goes to either the US data center or the Europe data center or the Asia Pacific data center. This is one of the other fun parts of doing DNS with AWS. So traffic distribution here is based on what is the lowest latency between AWS and the user. While this is, like I said, it's a fun feature to have because you can always redirect the user to the closest servers. But the problem that we've always seen is latency calculation can be inaccurate to a large extent. You will, when you're working with something like this, you will notice that the way you measure latency as a ping from your machine to the server is not how AWS measures it. Their values tend to be off by 15-20% at least, and that can produce issues every once in a while. There is then the next set of record types, which is IP based. So here you can directly say, hey, people coming from a particular IP address are the only ones who can be given a DNS entry. People coming from a particular set of IP addresses, like for example, if you are in the office and you want to connect to a particular domain for a service available on the cloud, you can do that with this. Multi-value is you can return multiple IP addresses for a particular domain. The difference is if you add a health check, this works slightly different from how a traditional DNS multi-value record works. In a traditional record, if you give 4 IP addresses to a domain, all 4 will be returned regardless. However, if you do a multi-value record on AWS with a health check, you can get 4 if all 4 are healthy, but if one of them goes down, then you will get only 3 records, right? So AWS can filter out records on its own. And we've been talking about health checks for so long, right? So this is what it is, right? So AWS Route 53 differs from your traditional bind and unbound and any other DNS resolver in one of the main aspects, which is health checks. So Route 53 as a service can actually go and monitor your services to see if they're healthy. And basis the health response, it can alter the DNS response for the clients that are asking it for information, right? So it can monitor an endpoint. It can monitor alarms defined on systems and services. It can do calculated health checks. So it can actually do is service 1 up plus service 1's latency is less than 500 ms plus database latency is less than 50 ms. And cumulatively, it can tell you if a host is healthy or not. Monitoring endpoints, like you can monitor it by protocol, you can monitor it by domain name, you can monitor it by IP, you can monitor it by URL. You can have advanced configurations for health checks, right? So you can figure out the time you need to you want to wait between 2 health checks. The lowest value is 10 seconds, I presume, but the maximum can be as high as 600 seconds. You can do string matching on responses. So if the service is returning something, you can actually do a check on the string in the header or in the payload saying, is it healthy, unhealthy? You can figure that out. You have failure thresholds. So having one failure does not mean the record needs to be eliminated. You can say that a service has to consistently fail 3 times, 5 times, 10 times for me to declare it a failure. You can also do inverted health checks. What that means is it will give a particular response as long as the service is down. If a service is up, then the health check fails and it actually stops doing it. So for example, you can do an inverted health check to handle a maintenance page. If you're doing a maintenance activity on your service, on your systems, you can have an IP address delivered, which will show a plain HTML page saying, hey, we are down for maintenance, as long as the actual service is not up. The moment the service is up, the IP of the service can be returned instead of the maintenance page. Again, you can do customizable regions. So you can always say that if a region is down, remove that region from my entire network. I want to redirect traffic to another region. So the last part, right? Why would you want to do something like this? Which app is a good candidate for a multi-region setup? The answer is it depends on how you architect them. But if you want to do active, this is what you need to keep in mind. You need to have stateless services. You need to have services with global data stores, or you need to have regional data store with a global replication setup. In this scenario, your data is always available globally. So you can actually flip a user over to a different service, and you're not doing any state-based user management. So your user can operate on another endpoint without even realizing, apart from a slightly slower response and increased latency time, right? Because, like, for example, if you're in India and the India data center is down, I can redirect a user to Singapore. But apart from latency, as long as my services are stateless, my data store is replicated, I don't have to worry about it. What apps are good candidates for multi-region? If you want an active passive setup, then you have active compute, and then you have a cold or a warm data store in a second region. So you always keep the compute ready, you keep the data store preferably warm, but you keep it cold, and then you cut over. What that means is the system is usually not handling traffic, but it is ready to, and then you just flip the DNS over. And this is how we would actually do it, right? If you want to do a global active or an active passive setup. So you have a client going to example.com. That's all the client is told. But there is either a geo-based load balancer or a latency-based router. So it goes to geoexample.com. From there, the user is sent to us.example.com, which is where you have an active standby setup. You have USA, you have USB. If US goes down, then the user will automatically flip to either EU or APAC, because the load balancer will check latency and geolocation, and one of these will be the default regions. In that scenario, the traffic can either be shared to EU A or EU B based on what is active. Same case for Asia Pacific, for example. Right? Do I have hints and tips? Yes. So small set of things that you want to understand very clearly is when you do, the fun part about DNS is at least with AWS, it gives you way more power than we are traditionally used to in a DNS environment. What that means is now, since the DNS service is actually talking back to your application and switching on and switching off applications, you need to understand your application architecture before jumping in. You can't directly say, okay, fine, I'll set up active without understanding how your state machine works, right? Route 53 unfortunately has one small problem, which is for a global DNS system, it can be accessed only in one AWS region. What that means is if that region has issues, you need to know how to handle AWS Route 53 from the backend, right? And one of the things that you do is you abuse your health checks in scenarios where you can't really figure out things, and there are some times where you have to force a cutover, right? And yes, you have AWS CLI commands, and that's how you literally abuse your health checks and keep your systems going. With that, my quick talk is done. 35 odd minutes. So I have, I think, 10 minutes left to take questions.
So any questions? Yeah, right. So one question from my side, considering the cloud, DNS as a web service on a cloud, how is the privacy assured in that?
Could you repeat that, because I'm trying to understand your question. Your question is loaded, so there is something more to it.
Okay, for example, we have the DOH and DOT service on a conventional DNS to ensure privacy. Right. Similarly, in route 53, how is the privacy ensured?
So privacy as a concept is standard in the DNS world, right? But once the DNS records are made available, right, and as long as they are diggable, I think it is straightforward. Nothing changes between AWS Route 53 and the rest of the world. When it comes to operating the DNS zone itself, you have a lot of permissions and controls to restrict who can access, who can make changes to the DNS zone file, who can touch it, who cannot. You have auditability, you have history tracking, you have change tracking, all of that built in.
Yep. Thank you. Any more questions?
So there's a question from MCF. Am I audible?
Yes.
Sir, actually, we are having our own DNS resolver here, and we are blocking various indicators of compromises as per the recommendations from like higher authorities, like certain and all. So sometimes what happens is like whenever like we are searching for something, like it will go to different name servers, right? So that name servers are blocked by IOC. Because of that, we are not able to like get the resolution of that websites. So any solution for that, sir, apart from whitelisting that?
No, so traditional, see, how AWS handles all these additional features is an internal AWS implementation. But as far as talking to the DNS server from outside or from a machine or a client is concerned, right? That is standard port 53.
That is allowed, sir, but various name servers like some AWS, like it will be going to some different domain names. So it will be while searching for name, it will go to like different domains, right? So few of those domains are actually blocked at our firewall level.
So that is something that AWS cannot do anything about. See, it is a name resolver. It is not a firewall. It is not a firewall controller either.
Okay. So
at the end of the day,
whitelist that from our firewall side, right?
yes. So the domain, see, if a domain is managed by AWS, or if you're talking to AWS's name servers to resolve a domain, and its job is to take a name of a domain and see if it knows and give you the IP address of that domain or whatever record it is that you're asking for. Apart from that, once the IP is in your hands, how traffic flows between your machine and that IP is on your side. That is not on AWS.
That part I understood. We are not able to get the IP sometimes because of this blocking.
So then resolvers. So what is happening is your internal resolver is blocking upstream requests.
Yes.
So that is something that has to be configured by your internal resolver. So what will happen is your internal resolver, instead of like for example, you're looking at example.com. You want to find out example.com. Your local DNS is a DNS resolver on your laptop is configured to use your Active Directories resolver, right? Now, our Active Directories resolver is returning 0000 for that example.com. It's either returning 0000 or it is returning an NX domain. Now, that is a configuration on your end and not something that AWS is even remotely involved in.
Okay. Okay, sir. Thanks.
Cool. Any further questions?
Okay, sir. I think no more questions, sir. Thank you very much, sir.
Thank you, people. Thanks a lot.
Thanks a lot. Bye.
Okay. Thank you. Bye bye.
Yeah, once again, good afternoon. The next session is on the tools, research work, tools which are the outcome of the research work that we have done as part of this project under COE-DNS. He's Mr. Shubham Goyal, and he has been working with us for past 4 years on DNS security. He'll be walking you through the tools. We actually have 4 types of tools for malicious domain detection, typo squatting, funny code detection, and name server health measurement. So he'll be demonstrating the tools, and with this slide, he'll be demonstrating the tools of the panel. Thank you.
Hello everyone, my name is Shubham Goyal. I am going to demonstration of tool developed by the COE-DNS team. The list of tools are 4 tools are there. The first tool is malicious domain checker. Malicious domain checker is a tool. It is used to detect whether a domain is a good domain or a bad domain. Bad domain means whose domain websites are doing a nefarious activity or a criminal activity. Good domains are those domains whose domains websites are doing a legitimate thing or benign thing. This tool is also integrated with our Rakshak DNS. Before I am going to explain what is Rakshak DNS, first in our daily use, we are using internet. If we are working in any organization and anything, that internet is very needed. For browsing an internet, that DNS is very crucial thing, or we can say without DNS that our internet is not work until unless you are not a geek person. So for that company, that one more thing that we need that security and privacy features for that DNS. So that our Rakshak DNS is a solution for this, that enterprise solution with all have the security and privacy features. And if you have more query, then please ask with our business development team. And now I am going to demonstrate the tools. That tool is available in our portal COE-DNSsecurity.in, and that in a tool section. Just give your domain name, whatever you want to see, like and give this captcha. It is malicious, or it is non-malicious. Just to classify the thing, it is malicious or non-malicious. Now, second tool is typo squatting checker. It is used by the attacker, and it is also used by the attacker. Attacker used for mislead the users. It is second name also, we can say it is a lookalike domain name. By this means it is approximate similar to that legitimate domain. You can see here that cclac.in instead of cdac.in means it is looking like a similar direct similar to cdac.in. Now I am going to demonstrate of typo squatting checker. Just give the domain name, whatever you want to give. It is a homoglyph, means it is looking like the similar of a domain name. It is not a original domain. If I am giving the original domain, what will happen? It is a homoglyph, means it is looking like the similar of a domain name. It is not a original domain. If I am giving the original domain, what will happen? It is not a original domain. If I am giving the original domain, what will happen? It is a homoglyph, means it is looking like the similar of a domain name. It is not a original domain. If I am giving the original domain, what will happen? It is the original domain. Okay. Now third tool is our DNS Health Analyzer. DNS Health Analyzer tool is giving the status of our authoritative name server of a particular domain name. That authoritative name servers, we know that all the John files and the records are kept in that authoritative name server. Here, that it will give the report based on some parameters. That parameters are number of 15 or 21. 15 is without DNSSEC, or 21 is including DNSSEC. I will explain how it is showing. Demonstration of Health Analyzer tool I will show. After giving the domain name, it will take some minimal time. Then it will give the report. That report will be in two sections. First section will define about the domain, and second section will define about the authoritative name servers of that particular domain. That two sections are there. That domain related thing, here it is showing how many name servers are there, means authoritative name servers are present for this domain name. In this, we are showing like here IPv4 address for that particular domain and IPv6 address of particular domain. Here we are checking that for that IP address, that reverse lookup is there or not. Reverse lookup means generally what we are doing, we are giving the domain name to the recursive resolver and we are getting the IP address of that domain name. But here we are checking that particular IP address is point out that same domain name or a different domain name. Now I am going to explain in that name server details. In this name server details also we are showing the IPv4 address, IPv6 address, and we are also showing the reverse lookup for that particular IPv4, IPv6 address of a name servers. Here these four things are saying about the reachability, means that our client or recursive resolver is reachable for that authoritative name server or not by a UDP or TCP protocols through a V4 or a V6 way. EDNS support is a extension mechanism of DNS support. It is saying, means generally what will happen in that DNS packet size is very minimal, but if it is if we are enable this EDNS support, whatever means it is giving, means it is sending the large packet of DNS through via UDP protocol. In this availability section, it is we are checking that authoritative name server is available or not for that particular domain name. Means maybe that is misconfigured that time because it is giving the, that list is given by the parent zone. Maybe that at time of given the domain name, maybe it is unpresent, means it is absent. SOA check. Here we are, means it is SOA check, means start of authority check. In this check, it is very important between the master and slave server. We are checking here that all the name servers have the same SOA file or not, or the value of that SOA in under that is in range or not according to RFCs. We are checking here. Zone transfer check, it is saying about, means we are checking that zone transfer is available or not. Zone transfer means zone transfer is happening between the master and the slave servers. And we are here checking that if anyone can attach with the master servers, then it is also a vulnerability. So that's we are here checking that zone transfer check. That recursion we are checking here, means recursion means when we are giving that domain name to the recursive resolver, it will check that that if recursive resolver have an IP address, then it will give revert back to IP address. Otherwise, it will follow the hierarchy. Or that when recursive resolver is going to the root server and coming answer back to the recursive resolver, that one-to-one it is to a recursion. We are checking that that authoritative name server by default that recursion is disallowed. So we are checking here like. NSEC means next secure record. We are checking here, means in some zone files that like subdomains are there. A.cdac.in, B.cdac.in, D.cdac.in. Maybe some client is asking about the C.cdac.in. What happened? At that time, some authoritative name server give the NX domain answer. But if NSEC is enabled, what it will do? It will give the D.cdac.in IP address. that authoritative answer check, it is saying, means we are checking that that answer is coming from the authoritative name server or somewhere else. Here we are checking the reverse lookup name server, reverse lookup domain from this particular authoritative name server. And resource record set match, we are checking that the whatever given by the NS record of the parent zone, it is same as whatever given by the authoritative name server is there or not. That round trip time we are checking here from the starting of the query to the end of the query till we are getting the answer, how much time it will take. So that total time is taking showing in this 124 millisecond. It is in millisecond. DNSSEC, as we know, that DNSSEC is a protocol which is given, which is gave that our authenticity and integrity between the hierarchy and the recursive resolver. So we are checking the DNSSEC also protocol. That is 15 parameters if DNSSEC is disabled. What if some sites DNSSEC is enabled? What will their parameters? 6 parameters are also there. It is taking some time. All are things same, just it has the DNSSEC enabled. So it is giving 6 parameters. Here we are checking the RS set size check. According to RFC, that our RS set size between less than or equal to that 1232 bytes. We are checking here that RS set size is same or not. That RS signability, we know that some that key pair have some lifeline. So we are checking that key signing is valid or not. Consistency and delegation signer record. Whatever given by the child zone to the parent zone, we are checking that DNSSEC file is how many keys are there. Or we are continuously checking that keys are changing or not. If it is changing, means something is wrong. Here DS record and TSK match. When we are sending some DS file to that delegation signer record to that parent, that some key ID is there. So we are checking that for that authoritative name server and that parent parent zone have same key is there or not. DNS key record consistency. Here we are checking the number of key files. Or DNSSEC strength, we are checking here cryptographic algorithm. Which cryptographic algorithm, how many keys are, means that keys, how many bits are we are using for generating a key like 2048 bit key, 4096 bit key, like that. Or if you want to generate, means if you want to download a report in PDF format, just download it from here. Based on this report, we are giving that report to MIT and Nixie also at the Corona time for COVID domain names, malicious COVID domain names. My next tool is domain Punicode identifier. This tool is also used by the attacker also, or benign also. We cannot say that only attacker can use this tool. What is actually Punicode? Punicode is nothing. It is just represent of IDNs. IDNs means internationalized domain name, Unicode character to a ASCII character. Like here, that Indian domain name, like in Hindi. That is Hindi domain name, IRF.bharat. It will convert in a ASCII character like this. This tool is giving the list of all Punicode for that particular domain name. I will show you 1 second. It will take some time for checking that all the Unicode domain for that domain. I will show you something now. This one. That you can check for Amazon.com how many Unicodes are available. Attacker what will do? It will means it will use this thing and just fooling the user. For this, when we are giving this A, just a SKY representation is A because it is a SKY character only. But when we are giving that that thing means that Unicode character, it will have some different value, but it is looking like a similar value only. Just a single character change, we can redirect to for a nefarious activity for that. That attacker can redirect to user for a nefarious activity. And thank you. That thing. So as said, these are the tools, and these are our tools briefly, and this is our website, coednssecurity.in, and all our activities are captured here. You can go to this tools menu and you can visit these tools and check these. And the intelligence that we have understood from these by developing these tools have been added to our public recursive resolver. So this is our public recursive resolver. It's open for the world. We are inviting world traffic, and per second about 8 queries are coming onto our recursive resolver, and it is hosted at this IP address. And anyone can configure this IP address at their Wi-Fi routers or internet gateways and divert their DNS queries onto our open resolver. Right. So this is one part, and for privacy issues, this is the DoH and DoT variant. Meaning this resolver will not know from where the query has originated. Okay, so that this is the privacy aware recursive resolver of ours. Okay, so we have been running this for about 4 years now, and we have gathered plenty of data using this recursive resolver, and these research outcomes are part of the data, are using the data that we have fetched from this recursive resolver and learned from those data. So that is one thing, and of course, if we go to the resources tab, there was one of someone had a question of how to start a DNS server or so. So we have the resources tab, and in the resources tab we have Bind, which is open source software. Bind software is open source software using which we can host a name server. Can be a recursive resolver, or it can be a authoritative name server too. So we have downloaded from the original distribution, and we have the license here. We have taken the permissions from them, and we have downloaded the download version is available at this link, and the respective manual, these clear steps to be followed to set up the recursive resolver are also captured as part of this. And we have done the last exercise in April 2022. I think we have to revise now. Every 6 months there is new revision of Bind which comes up. Our recursive resolver, which is running at this IP address in the public DNS server, is up to date, but this manual we haven't put it up, so we'll put up the recent manual as soon as possible. So those are our work, and yeah, so you can configure a DNS server using this. DoH or DoT is also configurable at this. Manual for that is present here, and we can also enhance the performance. Morning there was a session on DNS attacks where we were discussing about reflection, amplification, DDoS attack on DNS server. There are few configurations that can be done on a Bind server to cut down on these attacks. You can minimize the attacks to a far extent by automating, by doing some configurations on the Bind server. Those are also captured here as part of this. And there is other thing like we have a YouTube channel. Yeah, so InDreen is our YouTube channel, and this ongoing session and video of this ongoing session will be made available on this link.
And of course, if we go to the training tab, we have here previous trainings which are listed here. And one more entry will appear on this soon for the ongoing training which is happening. So this portal will be made up to date and contents will be available and people can definitely visit and make use of it and benefit from it. Right.
These tools are developed in machine learning based, AI based.
Yes, sir. Yes, sir. Just a minute. We need to have a setup ready for the next session. So we'll just get that ready and resume. It'll take 5 minutes. Let's see. So our next session is on DoH, DoT experiments over open source testbed. Okay, concerning privacy, DoH and DoT is important in the DNS ecosystem now. So the next session will be on DoH, DoT experiments over open source testbed by Dr. Mohit Tahlani. Dr. Mohit Tahlani is an associate professor of computer science and engineering at NIT Karnataka, Surathkal, and a member of Board of India Internet Engineering Society. He obtained his PhD in the area of congestion control mechanism for next generation internet from NITK, Surathkal. His areas of interest include network congestion control, deployments, named data networks, and distributed ledger technology. He has executed projects in these areas that have been funded by Intel, India, ABB Global Industries and Services, Robert Bosch Engineering, Epsilon India, Robosoft Technologies, Future V Technologies. Mohit Tahlani received the EMC Young Achiever of 2015 award from EMC Corporation Bangalore and Outstanding Young Professional Volunteer Award for of 2021 by IEEE Bangalore section. Mohit has contributed to open source projects for more than a decade. A packet scheduler developed by his team in NITK Surathkal to fight the buffer bloat problem got merged into the main line of the Linux kernel V version 5.6. He is a member of the steering committee of the NS3 consortium and co-maintainer of traffic control and TCP modules in NS3. He served as a member of the PEC for workshop on NS3 for the past 8 editions. Besides, he served as a mentor for Google Summer Code from 2017 to 2023 and was organization administrator for 2022. He also served as an organization administrator for NS3 participation in Google Coding during 2018 and 2019. He has 50 plus technical publications in peer-reviewed international conferences and journals. He is a reviewer of IEEE IoT, IEEE transactions on cloud computing, IEEE transactions on networking, Elsevier Journal of Networking and Computer Applications, Computer Communications, Inter Science Journals, IEEE Communication Letters, and has several other roles in IEEE and Springer conferences. He served as a guest editor for Annals of Telecommunications, Springer Journal. He is a senior member of IEEE and was a student activity chair of IEEE Mangalore subsection during 2015 to 2017, secretary during 2021, and a member of executive committee of IEEE Mangalore subsection for 7 years. He is currently the chair of IEEE Mangalore subsection and he is also a member of ACM. Thank you for joining, sir. It's over to you, sir.
Sure, thank you. Am I audible? Are you able to hear me?
Yes, sir. Yes, sir. Yes, sir. We can hear you.
Yes, sir. Are you able to share the screen, sir?
Yeah. So my student will be sharing the screen in a minute. First of all, I'll just like to say, so I have turned on my camera. I'm not sure whether you are able to see my stream coming in. Is my video working fine? I don't know. I'm asking you. It should be.
Yes, sir. It's all fine. We can see everything properly.
Okay. All right. Thanks. So first of all, I mean, Balaji, you are able to hear me, but I don't know whether the team at CDAC.
Sir, are you not able to unmute?
I'm speaking. I believe all others are able to hear. Most probably, I'm not sure. The speaker connection.
Let me check. So just a minute, sir. We are checking our speaker.
Yeah, thanks. All the online users are confirming that you all can hear me. So let's give them a minute. Once they fix the speaker issues, we can get started. Any luck?
Yes, sir. It's audible now, sir. Please continue, sir.
Okay, audible clearly now?
Yes, please.
Okay, all right. Okay, thank you everyone. First of all, a very good afternoon, and I apologize. I was supposed to be in person with all of you at CDAC. Oh, is my voice screaming around in the room? Is it? I can see some people putting the hands on the ears. Was I too loud? Well, let me try to speak softly from my side. I don't know. So I was supposed to be with all of you in person at CDAC. My apologies for not being able to come in person and be with all of you. And thank you for accommodating my request to be online. Am I coming through clearly? Is it audible clearly?
Yes, sir.
Yes, sir. Okay, thank you. So I have brought along with me one of my students who recently graduated. And it so happens that the invitation for this talk also came from Dr. Balaji from CDAC, and the student who is with me, his name is also Balaji, the one who is going to help me do the presentation today. So the topic that we have chosen is, we have chosen how to emulate the entire domain name system and the DNS over HTTPS on a single machine. Because one way that people have been doing these kind of experiments is by using virtual machines. But spinning virtual machines on a single computer can be very heavy. For example, if you want about 15 to 20 virtual machines to be put up, your one system probably would not be able to handle those resources. So what we have done is we have used something called Linux network namespaces. Balaji will be talking about it. And using Linux network namespaces, we have emulated the entire DNS architecture. And the purpose of doing this is because a lot of people are nowadays working on DOT, DNS over TLS, DOQ, DNS over Quick, DoH, DNS over HTTPS. And we wanted to create a playground for them so that they can play around with these kind of tools, and they don't need to spend money on infrastructure or need to have multiple machines to perform these experiments or spin off multiple virtual machines to perform these experiments. So Balaji, can you start sharing the screen? Let's see whether you have the access to share it. I'll confirm once you have it. Yeah.
I'm showing a Google slide. Is that visible?
You can go into the presentation mode. And I'll hand it over to you in a minute. Yeah. So like Balaji has given the title, DNS and DoH in namespaces. Yeah, Balaji, can you go for 1 minute for the agenda slide? Yeah, be there. So we'll be briefly talking about what are namespaces, particularly network namespaces, because in Linux kernel, we have about 8 different namespaces. Even C groups are there, right? So we are not going into that area. We are going to particularly talk on namespaces. All of you have been already listening throughout the day for DNS, so we'll not spend too much time on that. But then we will show how we have used bind9 and set them up in a single computer, multiple network namespaces. Then we'll talk about what is DNS over HTTPS in a quick one slide. Then show how we have used core DNS as a DoH server. And then we have an inbuilt utility which we have developed at NITK, which is open source utility, which is available for free for anybody to use and contribute. That utility is called Network Stack Tester. And we have made Python APIs for simplifying experiments on DNS and DoH. Balaji will be giving you a walkthrough of that as well. So Balaji, you can go to the first slide back again on the title slide. So Balaji Naidu actually graduated this year itself. He will be coming on November 4th to NITK to receive his degree. He graduated from Department of Electronics and Communication. I belong to Department of Computer Science and Engineering, but he was working with me on an industry-funded project wherein we were using DNS, DoH, and Linux network namespaces. So he worked with me for about 10 months, and he has a fantastic grip on the subject, and he has a demo ready to show to all of you. So I pass it on to Balaji. Balaji, you can take over from here. Over to you.
Thank you, sir. Just checking with everyone if I'm clearly audible and everyone can see my slides.
Yes, yes.
Yeah.
You're audible, sir. Yes.
Thank you. Yeah, as Mohit sir mentioned, I graduated from NITK this year. And yeah, we'll be, I think we covered the agenda on what exactly we are going to discuss. And I'll try to keep it hands-on as much as possible. And if anyone has any questions, feel free to interrupt and ask me anytime. Yeah, we'll start with what exactly network namespaces are. So yeah, network namespaces are basically abstraction over particular network resources in the kernel. Say, for example, when you have installed Ubuntu on your Linux on your laptop, you get certain things like a particular network interface card or the network stack itself, right? Where the packets come, it will take a particular path, and it will have certain data structures and basically other network resources for one particular laptop or one particular operating system. And if you want to use if you want to keep isolated network resources, say for example, you wanted to test something on 10 different machines, it's not very feasible to either get 10 physical machines and interconnect them with say Ethernet cables, or maybe using a Wi-Fi or something, or even spin up VMs, because that's going to be costly. So instead, namespaces is a inbuilt technology in Linux kernel, which is integrated with the mainline Linux kernel itself, where it abstracts particular network resources and isolates everything from each other. It's basically like a box inside your Linux kernel, which can't see the other box in the same space. So it will create its own networking stack completely, and it will isolate everything from the host network. So once you create a network namespace, and if you are inside the network namespace, it can't see any of the other networking resources which is on the host machine. Say you had 5 different physical network interface cards on the host machine, but once you're inside network namespace, you can't see any of those 5 network interface cards. So and this is one of the main technologies used in containers these days, be it Docker, LXD, all these container technologies, right? They want isolation from each other so that you can run thousands of containers on one physical machine. And main selling point of container is you need isolation. You don't need interaction from one container to other. Of course, you want interaction from a different way, but not the process themselves interacting between each other. So that's network namespaces. Yeah, I have added a quick slide on a visual slide on what a DNS query, how a DNS query looks like, right? I think you have been listening to DNS from morning, so I'll not spend much time on this. But basically, to just give an overview, whenever you do a query, it will go to your local resolver first, check if that's present in that in the local resolver's cache. If not, it then the local resolver says, okay, this is my name server, or this is where my DNS server is present. Can you fetch the IP addresses from there? Then it goes to the name server and it checks if it's present there. If not, it goes to a root name server asking, can you find IP of example.com? Then root server says, okay, I don't have the address with myself, but I can point you where you should get, or where you can get the result for your query, right? So it will say you should go to a .com name server, which is at this particular address, and it goes to that particular address. It's called a GTLD server. GTLD stands for global top level domain. And when it goes to that particular top level domain server, it asks, can you give me the IP of example.com domain name? Then GTLD server says, okay, it's in example.com name server, and it goes to a name server. Then it fetches the result and it travels through the stack back to your laptop or your physical machine, and you have the IP address now. So yeah, this is the entire life of a DNS query. It goes to resolver, name servers, GTLD name server, particular domain name server, and from there you get your IP address. Once you get the IP address, you'll cache it for a while based on how the record results are set. Yeah, so that was how a DNS query looks like. I have a simple visual of whatever I'm explained here, right? So I have a host machine which is connected to a DNS server called localNS, and localNS is connected to something called root name server, and root name server is connected to something called authoritative name server. I'm not sure if the diagram is very small, if it's okay. So yeah, I'm assuming it's fine, and we'll set up a similar architecture or the same architecture on Bind using namespaces. So Bind is a popular DNS server, popular open source DNS server, uh, which is actively being developed, and it gets the name Bind 9 because the current active version is version 9. So we'll set up the same architecture on using namespaces and run Bind servers on these and see. We have one particular domain called, we have added these records in the authoritative name server, and we'll try to fetch the records from this namespace. Think of this as 4 different machines, host being your laptop, local NS being your immediate DNS server, right? Say if you're using an internet service provider like Jio or Airtel, then they have their own DNS servers in their network. So this is similar to that DNS server in your ISP, and then that's internally connected to a root name server. Say for example, here I'm going to demo with a domain with a global top level domain called TCL. It doesn't exist. It's just for demo purpose. I'm using this GTLD so that no one gets confused with that. And the root name server is connected to authoritative name server where you have all the results, right? So for this particular domain name, this is the IP address which is currently mapped to. And say if I am the owner of ns1.test.tcl, then I'll have access to just authoritative name server or authNS in this particular diagram, where I can configure all my DNS record names here, saying my domain name's IP address is this. So so to do this experiment, ideally, if you wanted to do it with physical machines, you need a minimum 4 machines. So to avoid that, we'll be using network namespaces. And yeah, we'll start with that. I have all the configurations for this on my GitHub. I'll share the link at the end of the session so that people can try out later whenever they want. But can someone confirm that if they can see my terminal?
Yeah, visible. Yes.
Yeah. Okay, so I'm in a folder called bind9 right now, and as you saw earlier, we have four namespaces, right? One was host namespace, one is local NS, root NS, and the other one is auth NS. So we have all the configurations for each particular namespace in this particular directories, and we have a shell script called env.sh, which basically sets up the architecture which I showed you here. So it sets up all the four namespaces. It interconnects between all the four namespaces and creates a proper network for us, so that we don't have to struggle with dealing it with running the commands, each particular commands to create those. I'll briefly show how exactly env.sh looks. So yeah, this is just a command to clean up all the existing namespaces which I have earlier. You need not run this always. It's just to make sure I have a clean environment before I run a test setup. Here I'm adding four namespaces called host, local NS, root NS, auth NS. Once I have that, I'm setting up virtual Ethernet pairs between. I'm creating 3 virtual Ethernet pairs. So if I had to show that here, this is one virtual Ethernet pair. This is a virtual Ethernet 0 VETH1, and this is one pair. So I have 3 pairs, and I'm creating those 3 pairs here. Then once I create, assume virtual Ethernet pairs are like pipes. So now you have a pipe, and you have to connect each side of the pipe with a namespace, right? So that's what I'm doing here. I'm connecting one side of the pipe to namespace called host, and the other side of the pipe to a namespace called local NS. Similarly, I'm doing with the other 2 pairs as well. Once I have that, I'm assigning IP addresses to the virtual Ethernet interfaces. So I have different IP addresses for each of the interface names so that it won't clash. Again, I have added the IP addresses in the diagram as well. And once we have added IP address, we need to bring up the interface. It's similar to how you start your operating system. So you are starting this virtual interface, and yeah, these were particular virtual interfaces, and we are starting a loopback interface as well, so that if there is any connection for the interface itself, then it should have the loopback interface as well. It's the regular one which we have in Linux as well. And then I am enabling IP forwarding here, so that say if I send a packet from here to here, it should forward the packet from this interface to here. So I'm enabling IP forwarding on these 2 machines so that routing happens properly. And I'm adding a few routes so that routing is being taken care of. Does anyone have any questions on this? Can I proceed further? Okay, I'm assuming there are no questions. So let me clean up this. So we have in this namespace, as I said, we have all the configurations for each namespace here, and we have this directory called etc/netns, which stands for network namespace. Basically, we should keep all the configurations for whatever namespace we are trying to create in this particular path, so that when it's trying to create a namespace, say you have to override some configuration for that particular network namespace. I'm assuming you're all aware of a host file in your Linux machine, right? So this is my host file of the host machine. I have just few records, a few of the default records. But say now, when I'm trying to create a namespace called host, and I want different set of let me show resolve.conf. So it will be related to DNS as well. Yeah, so this is my resolve.conf or a configuration for your Linux machine, basically saying this is my resolver and you should use that particular resolver. And I'm saying use local resolver, which is on this IP address and this port. But say in my namespace, I want to use a different name server and I don't want to change my local machines configurations. Then you basically keep all the configurations under etc/netns and that particular host name, that particular network namespace name. So I'll just copy. I just copied whatever configurations I had in my local report to this particular directory name. Basically saying in authns, host, local ns, and root ns are the four namespaces I create, and all the configurations for those are inside that. Now I'll try to set up the topology itself, which was this. Basically creating four namespaces, virtual Ethernet pairs, and enabling enabling IP forwarding. Now to list this, you can just do ipnet10s list. So now it shows all the four namespaces which we created right now, and it has particular IDs along associated with them to uniquely identify that. So we have host, local NS, root NS, and auth NS. Now again coming back to this, as I said, we'll run bind 9 on these three machines, and assuming this is a laptop, we no need to run bind here because bind is, as I told you again, it's a DNS server, and we'll be running DNS server on the other three, and we'll have a local resolver in our laptop which will try to connect to this. But again, just to remind you, my laptop or this host namespace is just connected to this particular DNS server. It doesn't know it doesn't have any connection between this or this. So it'll whenever I make a DNS request, it should always it goes through this path and comes back in this path. Yeah, let me show the configurations first on how exactly it is configured. Later I'll show the demo as well. So first let me show host namespace, which just has a resolve.conf. As I said, I wanted to overwrite name server name here, which is saying you are connected to this particular DNS server, or but whenever I make a DNS request, just fetch results from this particular IP address or this particular DNS server. You might be familiar with configuring this with public servers like 8.8.8.8, which is Google's DNS server. If you want to override your ISP's DNS server, you can do that. So here I'm just saying you should, as a host machine, you should connect to 10.0.1.3, which is this machine. And I'll start up host. So you can get shells inside these network namespaces, similar to how you have containers and you can get shells there, or you have virtual machines and you can get shells there. You can run any type of any kind of command inside this particular namespace, and it will be isolated from the others. So now I have exec into, or I gotten a shell inside this particular namespace called host, and I'll leave it running for now. But if you want to just see the difference, so this is etc/resolve.conf inside the namespace, which says 10.0.1.3, but I haven't exec into or I haven't gotten a shell inside shell for any other namespace here. This is on the physical machine, which says name server is this, which is local machine, but on the host namespace, the name server is this, right? So now we saw configurations of host, and that's fine. Moving on to configurations of local NS, again we have a resolve.conf, but here we are saying name server is self. So if you get a query with from someone outside externally, or if you have a DNS query with yourself, you are running a DNS server yourself, so you should be able to get the answer from this particular IP address, which is local host. And we have a directory called bind where we configure the bind and server itself, right? You might see a lot of files here, but many of these are just the default configurations which you get, and you don't have to change anything here. So this is just to configure localhost. Similarly, this, so you don't have to worry about this. I'll just show what are the important files. So roots.hints is one particular file where we are hinting our DNS server saying, so we are looking at configuration of local name server, right? So this is a DNS server itself, but whenever you get a query where you don't have the results with yourself, we are trying to hint it, the root name server for you is in this particular IP address, which is 10.1.1.3. So going back to this, we are saying root server for TCL domain or TCL GTLD is in this particular address. So if you get any query for this domain and you don't have the results, just go to this IP address. And we just configure a zone here saying we have a type called hint, and the file for that is whatever I showed you earlier, the root.hints file, where we are just configuring hints for the local name server. And that is local name server. Let me just take into that and get a shell there as well. So I'm inside local name server here. Coming to root name server, which is connected to local name server, again has a folder or has a directory called bind, inside which again we have a lot of default files, but we'll not be looking at all of those. Instead, we have configured something here called a zone called root server.tcl. As I said, this is the root name server, right? So we have a zone for this, and the related file for that is here under etc bind zones, which is here, and root server db.rootserver.tcl. If we go here, and we have one more file called db.root saying for this root server, if you get any GTLD queries, or if you also don't have the results for .tcl domain, just contact this GTLD server, which is running on 10.0.0.3, which is our authoritative name server 10.0.0.3. That was db.root. db.root server.tcl says again, root server is itself 10.1.1.3. This is the root server, and if you get any queries for root queries, then you should be able to resolve those yourself. So now we'll exec into root server as well. Now we are inside root server shell here. Next, moving on to authns configurations. Again, we have a lot of default configurations. Coming to the particular configurations which we are interested in, we are saying we have a zone called TCL, and its particular file is here, and we have a zone called test.tcl, which is here, and GTLD servers, which is here. Now if we go to this, we have certain configurations here saying the name server for GTLD server.tcl is yourself, and the IP address for that, or IPv4 address in particular, because we are saying a record for this particular domain is 10.0.0.3, which is authns, which is the machine which we are in right now. And for db.tcl, again we have a root server for TCL is in this particular IP address which we saw earlier. And when it comes to one specific a domain name, right? Say for example, if I want to query ns1.test.tcl, and for a record for that, I have configured here itself. But ideally, in real world scenario, your authoritative name server will have this configured in a different machine. To avoid one more extra machine, I have just configured just for this one record. We don't have to spin up one more machine, right? So I have just configured it here. Now I'll just exec into authns as well. So now we have shells in all these four name servers, or all the four namespaces which we have created. Now what we want to do is we have to run bind servers on these three and do a DNS request from this, which DNS request for a particular domain name which is present in this server, and the DNS query should propagate from this machine all the way till here and come back here, right? So let me just start bind server, and this is the way named, even though the project name itself is bind, but the standard name used in all the Linux machines, or the binary name in Linux machines, is called named NAMED, and -G is just to show all the output logs inside this terminal itself instead of running it as a daemon. So I have started it on authns. I'll start it on root server. I'll start it on local server. And now, as I told you earlier, we have started bind and servers on these three. Now we want to do a query from here, right? So to do a query, okay, I think the command was not visible what I ran, but I'll just run again. Dig ns1.test.tcl. Can everyone see this command? I'm just running dig ns1.test.tcl. Dig is basically a command line utility to run DNS queries. But this is being taken, I mean, this is taken care for you in the browsers, in the browser itself. Basically, it will resolve all the domain name requests for you there. But now when I ran, I got a result saying answer for ns1.test.tcl is the A record for that is 10.2.1.7. Let's go back to the configuration again and see if that was the answer. So this was configured under authoritative name server, and we had said ns1.test.tcl. A record for that is this particular IP address, which we saw in the host namespace, right? So answer section says ns1.test.tcl is present here. So again, just to brief what we did, we ran authoritative name server ourselves, we ran a root name server ourselves, we ran a local name server ourselves, and we tried to query our local name server from our laptop or from our machine saying, fetch me domain name results of ns1.test.tcl, and it propagated the query all the way till authoritative name server and got the results back for us. So yeah, that's bind and configuration and how to run bind9 or bind on namespaces and get all the results. Anyone has any questions? If not, I'll move on to the next part, which is DoH and running, how to run DoH on or how to run DoH on namespaces.
Yeah, Balaji, can you hear me?
Yes, sir, I can hear.
Right. I just want to let the participants know that whatever Balaji explained right now, for example, you can see that he configured the entire topology, what DNS looks like in a single machine, and he showed a set of commands. And those who are new to Linux network namespaces, probably they would be a bit overwhelmed by looking at that there are so many commands to be written. But the good news is, as I told you, this is something that Balaji is showing raw on a single, on a single machine with, network namespaces. We have incorporated all of this into our emulator, which we are developing at NITK, and we have simplified it by using very simple Python APIs. So Balaji, you can also do one thing before you go to DoH. You can just quickly go through the APIs of how, same thing can be done in Nest. No need to run it because you can show the DoH demo, that is more important, but just show that how same architecture what you have drawn in the PPT, how it can be done using Python program, so that the audience who is listening does not feel that this is pretty complicated, but instead they have a sense that it is very easy to achieve. Yeah.
Yeah, sure, sir. So yeah, I showed
Not,
you guys.
not more than a minute or two. Just quickly go through the topology and just tell this is the Python APIs. That's it. Yeah.
Yes, sir. So we did all these things using shell script, right? So as sir mentioned, you have Python APIs to do all this. So what we are trying to do here is whatever the topology which we had earlier, right? We have host, local name server, root name server, and authoritative name server. Instead, we have 4 different authoritative name servers here, and we are saying configure authoritative name server and type is bind, and name for this authoritative name server is A1. Similarly, we are configuring 4. We are saying set up 6 different networks and connect all these networks using so basically what this is trying to do is here I showed how to set up the topology itself, and we had to run get a shell inside each of those namespaces and run individual commands ourselves, right? And even configure particular namespace saying your authoritative name server, and you should have this configuration and you should have those. So instead what Nest, which is a emulator, trying to do is we have all the same things inside a 100-line file here, which has plenty of comments as well. So it has more than 50 lines of comments itself. So we are saying for A1 authoritative name server, the FQDN is ns1.test.tcl and the IP address is this. For A2, you have a different domain called ns3.example.org and IP address is this. Similarly, others as well, right? And we are saying
the good part of this is that the JSON file that you are seeing that Balaji is showing, this JSON file is already provided. The user of our tool doesn't need to write it. All that they need to do is they need to probably configure the IP addresses, whatever they want, and other stuff that Balaji is showing. But the structure of the JSON and everything is provided beforehand. So that saves a lot of time. Yeah.
Yeah, you just have to edit whatever domain name you want and whatever IP address
and
you
that
want.
also, if you don't want in the beginning, you can just leave it as it is, whatever we have given. There's no need for you to change it all the time. And Balaji, you can also show where is this JSON file taken as an input, so we directly take it as an input.
So we have again we have an API for that calling import JSON, and we are just providing the file name, right? And we are saying just read this file and whatever configurations are in this file, we are converting those to all the bind and configurations which I explained you earlier here, where you saw a lot of default files here, right? Lot of all these files are not required, so we skip all those files in the Nest implementation which we have, so that you can write as simple code as possible and you don't have to do a lot of things there. So yeah, we are just setting up all those, and we are just starting. Okay, just start a name server, start authoritative name servers, and even to look up the particular IP address, right? I was doing dig. I had to get a shell in host machine and say, okay, run dig ns1.test.tcl, but you can do that in the Python command itself, saying h1 is your namespace name and you're saying forward lookup, just look up this particular IP address and get me the results, and it will print it for you. So you don't have to worry a lot about how to set up bind, how to set up namespaces yourself, and how to configure
it's all
those.
automated in this. And as he said, it's 113 lines, but more than 50% of these lines are only comments for people to understand what we are doing. You can see a lot of lines in the beginning, like first 50 lines are just showing the topology, and so many comments are there. So one thing that we wanted to do in this whole exercise was to ensure that the DNS emulation becomes easy. Yeah, that's it. I think Balaji, you can spend a little more time on DoH now. Yeah.
Yes, sir, sure. Yeah, so that was how to run DNS on namespaces. And coming to do, I just have a simple slide explaining what do is. So whatever you saw earlier, right? DNS is basically whenever you're trying to say, okay, fetch me IP address of google.com, it will create a UDP packet for you. UDP stands for user datagram protocol, and it basically adds all the DNS questions you have in that particular packet, and it sends to a DNS server. And whenever you receive back a packet, or whenever you receive back a answer saying this is the answer for your question, which was what is the IP address of google.com, but nothing in this packet is encrypted, right? So whenever I'm sending requests for something particular, if someone can anyone can just watch my network and see, okay, this guy is trying to go to SBI account, or he's trying to open trying to do some banking transaction, or trying to buy something online, or this is what particular his patterns look like, because your DNS requests are public as in it's not encrypted. Anyone who is on the network can see all your requests there because it's not encrypted. And there are chances, since it's a UDP packet, there are chances that your packet might not reach DNS server, and your laptop might be waiting for an answer from the DNS server itself. So people thought this was very insecure, and they wanted to encrypt the DNS packets as well. So they came up with something called DNS over HTTPS. So the underlying protocol for HTTPS again is just TCP. So you have a reliable connection there. So if even if your packet gets dropped, you have resilience so that you can get back your answer, or you can retransmit the question again asking for a packet. And very nice thing about DNS over HTTPS is the DNS request is over HTTPS, which is encrypted, and no one can see what exactly is inside that particular packet. So even if someone is on my network, and even if I'm browsing, say anything, say I'm shopping something, I'm watching a match or doing anything, they can't know what exactly I'm doing. They just see it's a HTTPS packet, but they can't know, okay, this guy is trying to go to this particular site or trying to buy something, all those things. So again, we are showing we have a local DoH proxy in your particular network, and which tries to connect over HTTPS to a DoH server. Currently, a lot of public infrastructure, or public internet providers, or big corporations have their DoH servers running publicly. For example, Google has its own DoH server publicly running. Cloudflare has its own DoH server running publicly. You can connect to those and make DoH requests yourself. And even the browsers which you have today, like say Chrome, be it Chrome, Brave, Internet Edge, Firefox, all these browsers also have support for DoH. So if you enable that option in your browser settings, it will send all the DNS requests over HTTPS, and you don't have to worry about about your privacy, or about someone looking at your packets or DNS requests from your name from your machine. Yeah, so coming to the hands-on part, we have a similar architecture or similar topology here as well. Instead, I have skipped one extra. So you can ignore the T2 application part here. You can just concentrate on these three machines, which is T1, recursive DNS resolver, and authoritative core DNS server. Earlier, we had extra namespace here called local NS. I have combined T1 and local NS here. So what I'm trying to achieve here is I have configured all my DNS records over here, which is authoritative core DNS server. Say uh, t2.test.tcl is this IP address. I'm configuring this particular information on here. And from T1 or this namespace, I'm trying to send a DoH request to this machine. And this internally sends a request to here and fetches the IP address, and we get IP address back.
Pallavi sir, sorry to disturb you. Mohit sir, because of the time constraint, you have only 5 minutes left, sir.
Sure. Sorry. I can just go to the demo of this and.
Please conclude in next 5 minutes.
Yeah, sure.
Thank you.
Again, we have configurations for all the namespaces here. You just have to. So I have copied all the configurations here. Now again, this is the env.sh is a similar script which we had shown earlier. So if I run that again, everything is configured now. Now I just have to take into authns and sorry. The name conventions in this particular is different. I think I'm calling it auth DNS instead of authns. So I'm running core DNS here saying core DNS and configuration. I'm providing a configuration file for that inside authority namespace, and similar to that, I'm running core DNS on recursive DNS server as well. Now, if I try to have exec into T1, which was similar to host from the earlier one, and now all I have to do is so we have this tool called DNS lookup, which will do DoH queries as well for us. So earlier, we had we were doing the lookup using dig, right? But now we are saying using DNS lookup tool, get me results of t2.test.tcl from this particular DoH server. The DoH server is ns1.test.tcl. It should be a DNS query. And if we run this, sorry, 1 second. Yeah, so it got the results for us saying for t2.test.tcl, 10.0.0.2 is the solution. And we saw logs here as well on the authoritative name server saying, showing the record came from here. The configurations for this is in my GitHub repo, which I'll share later. So again, as I showed in the earlier demo, we have support for emulating DNS on namespaces in Nest right now. So you can just check out this branch and run the examples provided. And I have added a few useful links, like how I have written a simple blog on how to set up DNS topologies using namespaces. Anyone who's new for network namespaces can check this. And this is the RFC for DoH itself. If you want to understand what is DoH and how exactly DoH works, internals of DoH, you can read this RFC. It's a well-written RFC. And this is my GitHub repo with all the configurations. I'll share the presentation later with the organizers. They can share it with everyone. And this is a link to the previous merge request which we had. So if you're interested to run DNS using Nest, you can just do that from there. And yeah, that's it from me. So that was how to run DNS and DoH on namespaces. So yeah, if you have any questions, you can ask now.
Yeah, thank you, Balaji sir, and Mohit sir. Any questions? Questions or any questions?
There is one question in the chat box, Balaji, if you want to take that.
Sure, sir. So the question is, what are the library used to implement name server in Python? So we are not using any external library as such. As I told you earlier, to create all the namespaces, the Nest itself is a tool which does create all the namespaces for you over APIs, over Python APIs. And to configure the DNS, say DNS files like be it bind9 or core DNS configuration file, then you don't need any external libraries to configure them, because all the configurations can be done in a simple file. So we are using the standard operating system, the OS library, to configure or open files and do configurations for the file. And to start the name server itself, we need those particular binaries. Say if we want to run core DNS, we want core DNS binary, or if we want to run bind, you want to have the named binary yourself. So we are not using any external libraries to implement this in Python. If that answers your questions, Nilin.
No, that's right. We don't use any dedicated Python library. We basically just use the command. We have a wrapper of Python on top of those commands to simplify the activities for the user. Okay, any further questions?
I don't think so, sir. Thanks a lot, sir, for joining. I know I troubled you.
No problem. No, not at all. In fact, I apologize. As I said, I also should have been there with all of you. Could not come in person. Second time, I'm not able to join. But I hope the session was useful.
Yeah, we will get another opportunity soon, and definitely thanks for sharing this wonderful knowledge. And I am sure that the participants here as well as online would be looking at this test bed, and they'll be gathering a lot of information. I think they'll also get back to you soon through either to us or through your direct presentation.
So we will share the slides with you, Dr. Balaji, and you can please feel free to share it with all of them. Any queries, we are more than happy to take. Yeah.
Definitely. And this just want to update you that whatever this session is, this actually will be edited and then will be put it in YouTube also, the same Green channel. So where your older videos are also there.
Name data networks. Yeah, sure. Sure. Feel free to put it on YouTube. No issues as such. Yeah. It's all open. The whole tool is open. Whatever we have built is openly available. Examples are openly available. So feel free to distribute.
Thank you, sir. Thanks a lot.
Thank you so much for giving us an opportunity. Yeah.
Yeah, definitely. Thanks. We'll catch up.
Yeah. Bye-bye.
So now I request our teams to show the demo now. The tools that
scanning and those type of analysis. Now, from the functionality point of view, we will just go to the asset part. Yeah. So it will do the scanning of the entire network. You can mention all the networks, what they call the size or whatever the configuration you want to provide. Either you can provide an entire network segment or depending on the requirement, you can give the input. Once that input is given, it will do the scanning. And once the scanning is done, it will capture all this information. You can see like what is the IP address, what is the operating system, its version, and what are the service running in that particular machine, and the vulnerabilities related to that. And it will give an indication like what are the top vulnerability in the what are the machines which are more vulnerable? For example, in the machine which IP address 2.104, it's 72 vulnerabilities. Out of that, 12 vulnerabilities are high and 48 are medium, and 12 are low. So, like this, you will get a complete picture of the machines and its vulnerabilities. And if you want to get a particular machine details, you can click it there. That in that particular machine, you will be able to see what are the service running, what are the criticality of that particular service, and what are the CDSS score. So this CDSS score is already known, it is a detailed information like we will be getting from the CD information also. Once it is connected to internet, we will be able to capture what are the vulnerabilities related to that ID provider. So this information we can get from the offline information hospital. So this particular information we are using for a zero trust model because once we are connecting to the device into the network, depending on the device vulnerability score, we will provide access or we will be denied that particular. Suppose that one device is totally vulnerable, then any request coming from that particular device will not be able to access. So that particular request will be denied. So suppose that today that device is secure and tomorrow some other services are running which is vulnerable. So that time what will happen is based on that current security procedure, the request will be denied. So that's what the actual zero trust principle. It will be considering the internal or external device, everything is the zero trust model. Nothing is implied trust. So whether it is inside network or outside network, there is no differentiation. So depending on the information or vulnerability posted, it will provide an access. So the typical firewall will be there, and on top of the firewall policy, it will be a dynamic policy. A trust score will be also part of the policy. If the trust score is very high, then it will get a full access. If the trust score is low, it will not get access. But the trust score is calculating in dynamic based on different network parameters and system parameters. So another feature what we are providing is that suppose if you have a static information related to the assets, generally any organization has to maintain the asset list. So that list also we can export into the system as a CSV file. For example, if you have Excel sheet that can be provided there. So using that information, we can derive other parameters like whether the system is under warranty, how many system is going to expire their warranty, all those types of papers can be generated. So these are another important information which can provide is the vulnerability defects. Yeah. So you might have seen that after the VLPT analysis, you will get a report. So what are the vulnerabilities, how you will be able to patch what are the service running, which service are more vulnerability and all. So that report, if we can assume like every day we are getting a report, then the advantage is that we can see the difference between different timeline, particular machine is it adding a service, and because of the service there is any vulnerability on that. So I think it's taking time for the latest report. Let's go for a report. Yeah. So complete profiling of a device is also possible. For example, if you want to analyze the particular machine, how many communications are there for a longer period of time, the entire profiling can be done. So we are capturing the entire data. from the communication point of view, it's not a packet level, it's a metadata we are capturing. So we are storing that data. Using that data, we can analyze the communication from a particular IP. For example, after attack, sometime we'll get information like this machine is communicated to some malicious server a long time back. So we should have a record for that. So this information can be used also that record. So we will be able to track the complete action from a particular machine. That's what we can see the IP-based tracking can be possible. At the same time, in the internal network, we are not using IP address, we are mapping it is based on MAC address. So even though in the DSCP scenario, the IP is changing, we will be able to track based on the MAC. I understood there is a possibility to change the MAC, but in the current context, we are not considering any MAC change in code somebody is using will not be able to detect. But if they are using an IP address, we can easily able to track it. The advantage is like if the same MAC is coming with the two different IP, two different time period, then we will be able to identify which machine it is actually generated. So this generating the record, you can see it's more than 20 page record. It will take some more time.
Not visible.
This is a report. You can see it's a vulnerability report. We can use it. This is a summary report from the entire network. What are the different types of vulnerabilities identified? What are the criticality and level? Then the individual IP, you can see different CVSS score based information providing and different IPs. Go to the top. IP address. You can see the IP address 2.50. So related to that IP, these are the vulnerability informations. So you can see even a single service itself have multiple vulnerabilities. So it will provide all the details. Okay, you can be able to filter based on some of the features. For example, I want to see only particular IPs information. Instead of going for the entire report, I can filter out a specific IP. And another thing is that if I want to see the more critical vulnerabilities, then you can filter based on the CVSF score also. CVSF score is starting from 0 to 10. 10 means a high vulnerability, 0 means a low vulnerability. So if you want to understand which machines are more vulnerable in the network, we can do the filtering also. So he's generating a report which has a CVSS score 9 to 10. You might be able to see, since it is doing a scanning, it will be able to identify the operating system and device type also. You can see these are switch related data whatever currently we are getting. That's what I mentioned. We are not running any agent in the system. Whatever traffic is generated and it's an active scanning we are doing. So we are communicating to the particular device and getting back the response. Based on that response, information is derived. So the report you can customize whatever way you want. So it can be used as a typical DAPT report, or it can be used as a summary report, or it can be used as a service level report also, or IP level report. So these are some of the basic features. So actually, as part of the zero trust, we have added more features to that. But this particular feature we are customizing as a solution: vulnerability assessment, as asset tracking, and security posture measurement tool. So this particular solution can be run as an appliance. So these appliance you can see here. It will be catered to 1 GPU's traffic as well as the entire network monitoring features. If any query related to this solution, device we can show it. Yeah, device I think it's complete. English. Connected now. Thank you. Yeah. This is you can explain this is the device currently we are getting all the time. So it's our 1G port and normal Ethernet ports we can use it. And we are continuing with the high-end device for 10G. They are going to be released by I think in 3 months.
So
That's our
we will really the vulnerability scan or it also do the penetration.
penetration test it's not doing. It's doing a vulnerability. It's not VAPT. It's not exactly for VAPT. That information can be used for internal particular.
And is it similar to SIM?
No. Because then it will collect logs and do analysis. Yes. Here it is the active scanning and will collect that information. But there is a passive traffic monitoring option.
This, it can go into the SIM. The data which is being collected can be actually sent to the SIM for further analysis.
SIM family it will take a log of this, but here the packet or mirror traffic is one.
Only monitor the traffic.
Yes, but the traffic monitoring is a passive monitoring.
Not active.
Not active. So you just give a direct traffic, it will do the monitoring. So using that, what we are doing is the new device detection is modified. For example, we already have identified IPs from the scanning. And in the network, you identify some IPs coming from the same range, then that will be a new IP. So once you identify the new IP, we can do a scanning immediately. So we will be able to verify whether the device is secured or not.
Even if in office environment or Wi-Fi environment, new mobiles are getting added, all those things can be did.
So like a BYOD environment. So we have a set of devices at present. Suddenly somebody is coming to install laptop. We want to allow that network, device to a network, but we will not be able to track whether it is a device is connected or not. Since it is connected into a network, we are using as a passive monitoring option. We will be able to identify that communication immediately. So then entire things as you see the profiling can be done. What service it's accessing, which server it is accessing, all those information is possibly captured.
Thank you, Dr.
Okay,
Martin.
thank you.
And anyone interested in these solutions, please write a mail to us, or you can reach us through RISE, RISE at cdac.in. That's the email ID. And you can actually
It can be given for a
pilot testing also. It can be deployed.
Project as part of that we can provide
Pilot deploy, and you can actually run it for a couple of weeks in your organization and see how it works. So definitely, sir. Definitely. I think I'll get back to you in the break.
I already did.
Sure. And now I request Mr. Jitendra Kumar. Yes, we have developed a email statements for as well as a sandbox to briefly explain what we have done.
Good afternoon.
Yep.
Shift F5.
Good afternoon, everyone. My name is Jitendra Kumar, and I have been working in the domain of email security for some time. Actually, I had a few slides regarding email security. Why is not moving? Not moving. Yeah, actually, I wanted to have few introductory introductory information for the email security. That because of the lack of time, I am skipping, and I would directly try to give a demo for a solution which we have developed it. And the solution name is Email Safeness Explorer. Many of you aware that email security is nothing but protection of your email infrastructure from the cyber attacks. Then nowadays, if you see that any organization has very larger surface attack surface area that is provided by the email, because many important communications which are happening nowadays, those important communications are happening using the email, and through email nowadays many such attacks are possible, like phishing attack, malware attacks, and like that. There are so many such attacks where primary source is the email. Then I would like to just introduce one solution. Its name is Email Safeness Explorer. By the name, if you say, it basically gives the score of your email. If a score is less, then you can say that the particular email may be a spam or phishing email. Here, I just want to give little information about spam. You know, spam is nothing but some unwanted mail that lands into your lands in your inbox without your permission. And phishing is also some unwanted mail, but it tries to steal your personal or sensitive information like a login ID, password, bank account password, something like this. They use some social engineering tricks for getting those information. Means basically this email safeness scorer, if your score is less, it says that either it's a spam or it may be phishing email. Then it provides the safeness score of your email and alert the user about possible phishing, scam, and then email spams. And this tool is privacy preserving because we are not sending your any data to the server. And if we are sending, those data are anonymized and unintelligible format. Even we are even sharing. And it is a machine learning based. It supports personalized model. Personalized model means you will have a personal model, personal machine learning model for yourself. And it's also support continuous learning, means it can be enriched with the new data sets. And clients are available for Thunderbird and Jimbra as a plugin. Then in this email safeness explorer, you have a feature like phishing detection, spam detection, malicious URL detection, personalized model, and continuous learning. Another tool which we are saying its name is spam box. By the name suggests that it nothing but it contains a certain email. Means it contains a list of emails. Those basically name may be misleading because I am saying a spam box. It's nothing like a spam box. It may contain your genuine email as well as spam emails also. And we are also providing a spam box client for sending your email data to the server. Basically, it works like this. From the spam box client, it does pre-processing, feature extraction, and then vector expression is generated, and then it sends to the spam box server. I think this is a snapshot. I will give you a demo. With that, it will be clear. Things will be clear. Okay, many of you would be using this Thunderbird. Have you heard about Thunderbird? Outlook Express. Actually, whenever we are using email, then we require certain email client. your email client can be web-based client as well, like Gmail and many others. And it can be a clients which are some clients which are made for such kind of things like Thunderbird and Outlook Express. This currently whatever I am using, it is a Thunderbird. In this Thunderbird, I have installed a plugin. This plugin is Safeness Explorer. If I click here, you can see for this particular email, score is very low. It means that it is either a spam or it may be a phishing email. And some other information also giving that unknown sender means the sender which has sent the mail that is not there in the contact list, and sender email authenticity could not be verified. This information I am getting through certain protocol like DNS and DoH. I'm not going very inside into that because DNS and DoH are certain protocols. It requires some more time. Just remember, like DNS and DoH are certain protocol that is used for protecting you from man-in-middle attack as well as spoofing attack in the case of email. And this is another email. This is also a spam email, and you can see here score is less. And this is a genuine email, and here you can see a score is high. Then with this, if a score is low, then it says that you should not do any action for that mail. Means that if some links are there in that email, you should not click it because it may be for the phishing. It may take you to the phishing website, and there they may hack your login ID and password. That's why you should be very much. It means if this is there, then you should be cautious. And certainly, because it is a machine learning based tool, and machine learning based tool always depends on the data sets. And for enriching the your model, you require new data sets. Then this spam box, using that you can share some data set like this. This is non-spam. Suppose this is a non-spam. Suppose this is a spam email, and this has come for you. If you want to share this to the spam box, you can mark it spam, and then I can accept it because you are sharing, and then further you can report it. Once you have reported, your reported email will come here in a spam box server. And further, if you log in, you can see your contribution. Here, this is your contribution. Then this spam box provides you two things. One is the continuous learning and one is the personalized model. Suppose if you want to ask for a personalized model, suppose you are asking for a personalized model, then you can request it, and this personalized model will give you a personalized model for you. It means that it has got intelligence for mail you are receiving. Then it has got support for giving you the personalized model, and I'm saying it provides you the continuous learning because every time a new data set is coming, and this new data set can be added along with the global data set, and each can be, and every time we can create a new model which has got new intelligence, means intelligence for the new email patterns. That's how it, because of this spam box, we are having support for the personalized model as well as continuous learning. Then this is the two tool which I have explained you briefly, and that's it from my side. Thank you.
Because more alert can actually give more alert to the end user. Of any risk for the user. So it will actually even if a user is going to be exploited of social engineering attacks, this tool has the potential to stop it. So that way, as an additional layer of defense, this tool can be used. And of course, your privacy and all those things are very well protected. And of course, we use machine learning and intelligence, continuous learning algorithms. So the accuracy keeps improving. Obviously, we cannot be 100% right, but at least we are aiming for a very closer accuracy. But at least some sort of alert can be there. So for any novice user, anything which is related to financial information, it can be easily alerted. Any kind of scams, it can be alerted. So this kind of solution actually is a very well suited solution for it. So that's it from my side. Any questions here for this general questions from any of these two sessions, both online participants or offline participants? Any chat? Okay. So if not, I request definitely all these sessions, the presentations, everything will be shared in our website, and all the videos are also will be made available on the YouTube video channel. So that will be done actually. I also request all of you to give your valuable feedback because that will help us to improve the session. Email regarding the feedback has been actually sent to your email, so you can open the link and we can connect with you. We want to. Yes. Sorry, I'm not able to get it. You can make the interaction is available for evaluation. So you can actually do the complete. Yeah, you can explore out loud. Only Zimra and the Thunderbolt right now. Right. Yeah, right, sir. Better to organization so that it will become easier for us.
Each of the attendees here, you have received a link on your emails, and you can please give your valuable feedback. And there is a shared screen. The QR code is available. One can scan even the QR code and give the feedback. Yeah, the online participants can scan the QR code and give their feedback. We are ending the online session. The online attendees can please scan the QR code, fill up the feedback form, and submit. We are now closing the online session. Thank you very much for your participation.
Thank you all the online participants who have joined here. I hope you have found this session to be very useful, and we like to meet all of you in person in the future session. Thank you. Thank you all.